Session 3 Chemistry. So in the particular session we'll cover our DNF block. So NCERT line by line read பண்ண போறோம், and then in text questions, out text questions, and then finally if time permits we'll try solving our previous year questions as well. So let's get started now. DNF block elements. So first things first, let's see the objectives. So after studying this unit, you will be able to learn the positions of the DNF block elements in the periodic table, know the electronic configurations, appreciate the relative stability of various oxidation states in terms of their electrode potential values, describe the preparation, properties, structures of the important compounds of K2Cr2O7 and KMnO4, understand the general characteristics of the DNF block elements and the general horizontal and group trends in them. Describe the properties of the F block elements and then give a comparative account of the lanthanoids and actinoids with respect to their electronic configurations, oxidation states, and chemical behavior. So that's it. We'll talk about the position, we'll know the electronic configuration, we'll talk about the oxidation states, and we'll have two important compounds of K2Cr2O7, that is potassium dichromate and potassium manganese. KMnO4, and then we'll understand certain characteristics and the properties of the elements of DNF block. Iron, copper, silver, and gold are among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as thorium, palladium, uranium are proving excellent sources of nuclear energy in modern times. So let's get into it. The d block of the periodic table contains the elements of the groups 3 to 12 in which the d orbitals are progressively filled in each of the 4 long periods. The f block consists of elements in which the 4f and 5f orbitals are progressively filled. So basically d block it covers up the groups of 3 to 12 in which we'll have and then d orbitals are basically filled progressively, and then in f case we will fill that 4f and 5f orbitals. They are placed in a separate panel at the bottom of the periodic table. The names transition metals and the inner transition metals are often used to refer to the elements of DNF block. There are mainly 4 series of the transition metals: the 3D series from scandium to zinc, the 4D series from ytterbium to cadmium, the 5D series from lanthanum and hafnium to hydrogyrum, that is mercury, and the 6D series of actinium and rutherfordium to Cn. So the 2 series of the inner transition metals, the 4f cerium to lutetium and 5f thorium to lawrencium, are known as the lanthanoids and actinoids respectively. Moving down, originally the name transition metals were derived from the fact that their chemical properties are transitional between those of S and P block elements. Now, according to the IUPAC, the transition metals are defined as metals which have incomplete d subshell either in the neutral or in their ions. So zinc, cadmium, and mercury of group 12 have full D10 configurations, which means that it is not regarded as a transition metal. The presence of partly filled d or f orbitals in their atoms makes transition elements different from that of the non-transition elements. Hence, transition elements and their compounds are studied separately. The usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements as well. The various precious metals such as silver, gold, and platinum, and industrially important metals like iron and copper and titanium belong to the transition metal series. In this unit, we shall first deal with the electronic configuration, occurrence, and general characteristic of the transition elements, with special emphasis on the trends in the properties of the first row 3D series, and along with the preparation and properties of some important compounds. This will be followed by consideration of certain general aspects such as electronic configurations, oxidation states, and chemical reactivity of the inner transition metals. Moving down, we'll talk about the transition elements of that is the D block elements. The D block occupies the large middle section of the periodic table, flanked between the S and P blocks in the periodic table. The D blocks of the penultimate energy level of the atom receive electrons, giving rise to the 4 series of transition metals, that is the 3D, 4D, 5D, and 6D. So basically, this particular D block it is going to the electrons going to be filled in progressively in the D block of our energy levels, and it is particularly filling the penultimate energy level D block, which means that so it starts from the 4f period. The series are termed as 3D, 4D, 5D series, right? And it's actually a middle section occupying between the S and P blocks. All these transition series of transition elements are shown in table 8.1. So we'll talk about the electronic configurations. In general, the electronic configuration of the outer orbitals of these elements is n-1 d10 ns1 to 2. So in the particular case, penultimate energy level we'll have 1 to 10 configuration for in d orbital, and then in s orbital of the ultimate Penel energy level we'll have 1 or 2 electrons, except for palladium. In palladium alone, we'll have 4d10 and then we'll have 5s0. The n minus 1 stands for the inner d orbitals, which may have 1 to 10 electrons, and the outermost ns orbital have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between the n minus 1d and ns2. So, basically, in this generalization, we cannot give it as it is. There's only a little energy difference. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configurations of chromium and copper in the 3D series. So basically என்ன சொல்ல வராங்க அப்படின்னா, completely and half filled cells it will be having a relatively more stable configuration, which means that stable configuration or okay, so basically sorry for the inconvenience. So since the half filled and the completely filled orbitals have stabler configurations and atoms tends to move towards the stabler configurations themselves, so adan karanamaga we will have certain exceptions, as in the case of in 3D series where we'll have an exception in chromium and copper, and similarly in case of chromium we'll have a 3D5 4s1 type of configuration, and in instead of a 3D4 4s2, because that the energy gap between the two sets is relatively smaller, and to obtain a stable configuration, that is a half filled configuration, basically the d orbital obtains one electron from the s orbital, finally forms a 3d5 and 4s1 configuration. Similarly, in case of copper, the configuration of 3d10 4s1 and not 3d9 and 4s2, the ground state electronic configurations of the outer orbitals of the transition elements are given in table 8.1. Okay, fine. So basically we have been given with the table 8.1. So this is something we'll have to remember. Okay, fine, great. It would be better if we remember actually. Yes, 1 minute. So let's get started. So the first series, the easier one, that's scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Starting from 21, ending at 2030. So if I'll have to write the configurations, as you all might know, only there will be two exceptions, one at chromium, the other one at copper, where chromium is expected to have 3d5 3d4 4s2, but it has obtained a configuration of 3d5 4s1 due to relative stability of the half fill configuration. And similarly we have copper, where we will have 3d10 4s1 instead of 3d9 4s2, due to the fact that D is obtaining a completely filled configuration. Henceforth, these are the two exceptions that we will see in this particular series. Moving down, yeah, ytterbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium. So first, I'm gonna remember the sequence of elements: ytterbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, and then I'll have silver and cadmium. So for ytterbium, it starts with basically 39 and it's ending at cadmium. Okay, let me just write it one by one. Ytterbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. Yes. So ytterbium starts with 39, 40, 41, 42, 43, 44, 45, 46, 47, and 48. Yes, which means that I will start my configurations with 5s2 4d1, 5s2 4d1, 5s2 4d2, and this guy NeoBM is having an exception over here. It is expected, so let me write expected in green. So it is expected to have 5s2, no, let me just change the color. So it is expected to have 5s2 4d3, but it turns out to have 5s uh, 5s1 4d4. I don't know why. So that's the first exception, NeoBM. And molybdenum, it is expected to have 5s2 4d4, but it turns out to have 5s1 4d5. But this is fine because this guy is trying to obtain a half-filled configuration. That's great. But surprisingly, in the next case, it must have 5s2 4d5, but it turns out to have 5s1 4d6, and this is actually surprising me, brother. Fine, moving down, we'll have the configurations filled as okay. Next expected என்னதுப்பா 5s2 4d6, ஆனால் நமக்கு வருவதோ 5s1 4d7. அடுத்து இங்கே வருவது 5s2 4d8, ஆனால் நமக்கு வருவதோ for rhodium, I mean 4d7 actually, but what I'm obtaining is 5s1 4d8. And palladium is the most extreme case where we'll have no electron in the s orbital of fifth LRG level and the completely filled d orbital is obtained. And in argentum, as expected, it should have 5s1 4d10, as it is obtaining a completely filled d configuration. And then finally 5s2 4d10 for cadmium. ஸோ இதில் இருக்கிற ஒரு சில முக்கியமான உருப்படியாக இருக்கிற நபர்கள் யாருன்னா இட்ரிபியம். ஸோ 4D சீரீஸை பொறுத்த வரைக்கும் ப்ராப்பர் கான்ஃபிகரேஷன் ஃபாலோ பண்ணுறது இட்ரிபியம், ஜிர்கோனியம் மற்றும் கேட்மியம் மட்டும்தான். அண்ட் அதிலே மோஸ்ட் எக்ஸ்ட்ரீம் கேஸ் வந்துட்டு எக்ஸ்ட்ரீம் கேஸில் வி ஹாவ் பலாடியம், வேறு பலாடியம் ஹேஸ் நோ எலக்ட்ரான்ஸ் இன் த எஸ் ஆர்பிட்டால். மூவிங் டவுன், வில் டாக் அபவுட் 3D சீரீஸ். 3D சீரீஸ் அப்படின்றது I mean third series, that's a 5D series. Okay, fine. So it starts with lanthanum and we'll have hafnium, tantalum, wolfram, rhenium, osmium, iridium, platinum, and aurum and hydrargyrum. Right to okay. So first நம்ம ரிமெம்பர் பண்ணுறது ரொம்ப முக்கியம். Ytterbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. அடுத்து வந்துட்டு lanthanum, hafnium, tantalum, wolfram, osmium, iridium, platinum. I think I'm doing something wrong. I have rhenium as well. Okay, rhenium இருக்குமா? Rhenium, wolfram, rhenium, osmium, iridium, platinum, gold, and then we have mercury. Yes, so let me just remember it again. Lanthanum and hafnium, tantalum, wolfram, rhenium, osmium, iridium, platinum, gold, and we have mercury. Mercury is hydrargyrum. Yes, so எதிர்பார்த்ததை போல் இவருக்கு 6s2 5d1 என்ற ஒரு கான்ஃபிகரேஷன் இருக்க வேண்டும். அண்ட் 6s2 5d1 நான் ஏன் எழுதுறேன்னா ஃபார் மை கன்வீனியன்ஸ், ஜஸ்ட் ஃபார் மை ரிமெம்பரன்ஸ், பட் ஆக்சுவலி இட் ஷுட் பி ரிட்டன் as 5d1 and 6s2. okay, and then we have hafnium. As expected, it is having 6s2 5d2. And then we have tantalum should be having 6s2 5d3, and I think it is the same. And then wolfram, it should be having 6s2 6s1 5d5, but it turns out to have 6s2 5d4 itself. And rhenium, it is going as usual 6s2 5d5, and then osmium has 6s2 5d6, and iridium has 6s2 5d7, and now we are obtaining the jump. என்னன்னா பிளாட்டினமில் 6s1 5d9 வருது instead of 6s2 5d8. ஸோ இவர் இஸ் டேர்னிங் அவுட் டு பி அன் எக்ஸப்ஷன். ஸோ தேர்ட் சீரீஸை பொறுத்த வரைக்கும் பிளாட்டினம் ஒரு எக்ஸப்ஷன், அண்ட் ஆப்வியஸ்லி கோல்டு வில் ஆல்சோ பி அன் எக்ஸப்ஷன் due to it obtaining an completely filled d orbital. ஸோ ஃபஸ்ட்டு சீரீஸை பொறுத்த வரைக்கும் குரோமியம் மற்றும் காப்பர். செகண்ட் சீரீஸை பொறுத்த வரைக்கும் வி ஹாவ் கன்ஃபர்மேஷன்ஸாகவே வந்துட்டு வீல் ஹாவ் ப்ராப்பரான லைக் எக்ஸ்பெக்டடாக இருக்கிறது வந்து யுட்ரபியம், சிர்கோனியம் மற்றும் கேட்மியம் மட்டும்தான். அண்ட் அதில் எக்ஸ்ட்ரீம் ஸ்பெஷல் கேஸ் வந்து பலாடியம். அண்ட் தேர்ட் ஒனில் முக்கியமாக நம்ம ஞாபகம் வச்சுக்க வேண்டியது இட்ஸ் கோயிங் டு பி பிளாட்டினம் அண்ட் கோல்டு, பிளாட்டினம் அண்ட் aurum. And we have fourth series as well. I'm not okay. Fourth series பொறுத்த வரைக்கும் ராட்ஜீனியம் அப்படின்ற அந்த பர்டிகுலர் எலிமெண்ட் மட்டும்தான் இட்ஸ் கோயிங் டு பி அவர் exceptional case. மற்ற எல்லாமே இட்ஸ் கோயிங் டு பி ஃபைன் ஆக்சுவலி. தட்ஸ் ஆக்டினம், ருதர்ஃபோர்டியம். Yes. So the electronic configurations of the outer orbitals of zinc, cadmium, mercury and Cn is represented by the general formula n-1 d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in the common oxidation state. Therefore, they are not regarded as transition elements. So zinc, cadmium, mercury மற்றும் candla, அதாவது transition elements அப்படின்றது the one which has completely, an incomplete d orbital in its atomic state, that is in its ground state as well as in its ionic state or in its ionic state. ஆனால் இந்த பர்டிகுலர் கேஸில் ஜிங்க், கேட்மியம், மர்க்குரி மற்றும் கேன்லா இதெல்லாமே வந்துட்டு they are not having like incomplete states even in their oxidation states, means they are not transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, hence they are more influenced by the surroundings as well as affect the atoms or molecules surrounding them. அதாவது டி ஆர்பிட்டால்ஸோட ப்ரொட்ரூடிங் நேச்சர் வந்துட்டு அதிகமாக இருக்குன்ற காரணத்தினால மற்ற சரௌண்டிங்ஸில் இருக்க ஆட்டம்ஸ்னாலேயும் இன்ஃப்ளூயன்ஸ் ஆகப்படும். அண்ட் அதே சமயத்தில் மற்ற ஆட்டம்ஸ் சரௌண்டிங்ஸில் இருக்க மற்ற ஆட்டம்ஸையும் வந்துட்டு இட் இஸ் கோன் இன்ஃப்ளூயன்ஸ்ன்றதா சொல்கிறாங்க. இன் சம் ரெஸ்பெக்ட்ஸ் ions of a given dn configuration n is equal to 1 to 9 have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristic properties such as display of variety of oxidation states. ஸோ இப்போ பேசிக்கலி நம்மளோட டி ஆர்பிட்டால் டி பிளாக்ல இருக்க எலிமெண்ட்ஸ்க்கு வந்து தேர் ஆர் சர்டன் கேரக்டரிஸ்டிக் ப்ராப்பர்ட்டிஸ். ஏன் அப்படின்னா தே ஆர் ஹேவிங் ப்ராப்பர்ட்டி ஆஃப் ப்ரொட்ரூடிங் இன்டு அதர் எலிமெண்ட்ஸ் atoms due to their shape or whatever. So they are able to display a variety of oxidation state, form colored compounds, enter into complex formation with variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. So moving down, there are greater similarities in the properties of the transition elements of a horizontal row in contrast to the non-transition elements. அதாவது நான் டிரான்சிஷன் எலிமெண்ட்ஸை பொறுத்த வரைக்கும் ஒன்லி குரூப் சிமிலாரிட்டிஸ் தான் இருக்கும். ஆனால் நம்ம டிரான்சிஷன் எலிமெண்ட்ஸில் வில் ஹாவ் சிமிலாரிட்டிஸ் ஈவன் இன் த ஹாரிசான்டல் ரோஸ், தட் இஸ் இன் த பீரியட்ஸ் ஆஸ் வெல். So we shall first study the general characteristics and their trends in the horizontal rows and then consider some group similarities. Oh. வெளிய போட்டான். Okay, general properties of the transition elements, D block. So first we will talk about the physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity and metallic luster. With exceptions of zinc, cadmium, mercury and manganese, they have one or more typical metallic structures. So basically we will be talking about the lattice structures of the transition elements one by one. இப்போ பேசிக்கலி நம்ம இது ஞாபகம் வச்சுக்கிறதுக்காக we will just divide it into groups. வெளி அல்வாடா. ஓகே, ஸோ ஓகே, நம்மளோட பிரேக்கிங் எப்படி இருக்குன்றதை பார்ப்போம். ஃபர்ஸ்ட் ஆஃப் ஆல், ஃபர்ஸ்ட் டூ குரூப்ஸ், அதாவது தேர்ட் அண்ட் ஃபோர்த் குரூப்ஸ் அப்படின்றத ஐ வில் compile as one group that is having HCP or BCC structures. Next, second, fifth and sixth group, vanadium and chromium இருக்கிற groups எல்லாம் வந்துட்டு it's going to have only one structure, that is BCC. And then manganese Fe இருக்கிற groups வந்துட்டு 7 and 8. 7 and 8 groups எல்லாம் வந்துட்டு பார்த்தீங்கன்னா it is having HCP structure. And with exception of manganese மட்டும் there will not be any it will not have more than one structures. Okay, and then for cobalt, nickel, copper, that is 9, 10, 11 groups will have CCP structure. And then finally the zinc, cadmium, mercury will not have any structure. So as you can see, scandium, titanium groups, the third and fourth group has no structure, has HCP or BCC. Second group has BCC, third element has HCP structure, and the fourth grouping has CCP structure, and final grouping doesn't have any structure. So இதுதான் நம்ம ஞாபகம் வச்சுக்கிற கீவேர்டு வந்துட்டு 3223 2223. Yes. Okay, so BCC means body centered, HCP means hexagonal closed packed, CCP means cubic closed packed, and X is a typical metallic structure. According to that particular, it's not a generic structure, it's a typical metallic structure. Moving down, the transition metals with the exception of zinc, cadmium, mercury are very hard and have low volatility. Their melting and boiling points are high. ஸோ அதாவது இந்த ஜிங்க், கேட்மியம், மெர்க்குரி இதெல்லாம் தவிர்த்து மற்ற எல்லா டிரான்சிஷன் எலிமெண்ட்டுமே ரொம்ப ஹார்டாகவும் இருக்கும், வாலட்டாலிட்டி ரொம்ப ரொம்ப குறைவாக இருக்கும் அப்படின்னு சொல்கிறாங்க. இந்த மெல்டிங் அண்ட் பாயிலிங் பாயிண்ட்ஸ் கண்டிப்பாக அது அதிகமாக இருக்கும். The figure 8.1 depicts the melting points of the transition metals belonging to 3D, 4D and 5D series. ஸோ 3D, 4D, 5D சீரீஸில் இருக்க எலிமெண்ட்ஸை பற்றின ஒரு டிபிக்ஷன், அதோட மெல்டிங் பாயிண்ட்ஸை பற்றி பார்க்குறோம். The high melting points of these elements are attributed to the involvement of a greater number of n-1d in addition. Orbitals உடைய involvement அதிகமாக comparison of the second series. Comparison shows that the heavy transition analysis அதிகமாக சொல்றாங்க. Moving down, variation in atomic and ionic sizes of atomic number அதிகமாக ரேடியஸ் உடைய வேல்யூ வந்து கம்மியாகும் அப்படின்ற சொல்றாங்க. இதுக்கான காரணம் என்னன்னா, டி ஆர்பிட்டாலில் ஒவ்வொரு முறையும் அட்டாமிக் நம்பர் அதிகமாகும் பொழுது இந்த நம்பர் ஆஃப் எலக்ட்ரான்ஸ் இந்த டி செல் இஸ் பிகமிங் பிக்கர். அண்ட் டி ஆர்பிட்டால் எலக்ட்ரான்ஸ்க்கு வந்து சின்ஸ் இட் ஹேஸ் அ புவர் ஷீல்டிங் எஃபெக்ட், டியூ டு தட் ஃபேக்ட் இந்த நியூக்ளியர் சார்ஜ் வந்து இட் இஸ் ஆல்சோ இன்க்ரீசிங். இப்போ நியூக்ளியர் சார்ஜ் வந்துட்டு இன்க்ரீஸ் ஆனால் இப்போ ஷீல்டிங் எஃபெக்ட் கண்டிப்பாக கம்மியாகும் அண்ட் இட் இஸ் நாட் தட் எஃபெக்டிவ். அப்போ கான்சிக்வெண்ட்லி ரேடியஸ் வந்து இட் இஸ் கோனா டிக்ரீஸ். இதுதான் திஸ் இஸ் வாட் ஆக்சுவலி ஹேப்பன்ஸ் இன் திஸ் பர்டிகுலர் டி சீரீஸ். ஆனால் த வேரியேஷன் இஸ் நாட் drastic. There's only a very quite changes in this particular variation. So an interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. The curves in figure 8.3 show an increase from the first to the second series of the elements, but the radii of the third series are virtually the same as those of the corresponding members of the second series. This phenomenon is associated with the intervention of the 4f orbital, which must be filled before the 5d series of the elements begin. The filling of 4f before the 5d orbital results in a regular decrease in the atomic radii called the lanthanide contraction, which essentially compensates for the expected increase in the atomic size with increasing atomic number. ஸோ பேசிக்கலி என்ன நடக்குது அப்படின்னா, நம்மளுடைய குரூப் ட்ரெண்ட்ஸ் பார்த்துட்டோம், பீரியட் ட்ரெண்ட்ஸ் பார்த்துட்டோம். பீரியட் ட்ரெண்ட்ஸை பொறுத்த வரைக்கும் தேர் இஸ் நாட் வெரி மச் வேரியேஷன் இந்த அட்டாமிக் இந்த ரேடியை. பட் இஃப் ஐ எம் கம்பேரிங் இன் குரூப்ஸ் குரூப் வைஸ் செக் பண்ணும் பொழுது 5D and 4D and 5D உடைய அட்டாமிக் ரேடியை டிஃப்ரென்ஸ் அப்படின்றது இட்ஸ் நாட் தட் பிக். அதாவது தே ஆர் குவைட் சிமிலர். இதுக்கான காரணம் என்ன அப்படின்னா, பிஃபோர் ஃபில்லிங் ஆஃப் த 5D சீரீஸ் வில் ஹாவ் டு ஃபில் த 4F சீரீஸை ஃபில் பண்ணுறதுக்கு காரணமாக இட் இஸ் கான்ட்ரிபியூட்டிங் டுவர்ட்ஸ் ஹையர் நெட் எலக்ட்ரோஸ்டாட்டிக் அட்ராக்ஷன் டுவர்ட்ஸ் த நியூக்ளியர்ஸ், which means that it is compensating for the expected increase in the atomic size. So that is what we call as the lanthanide contraction. So the net result of the lanthanide contraction is that the second and the third D series exhibit similar radii. So as you can see, zirconium and hafnium, they have nearly the same atomic radii and have very similar physical and chemical properties, much more than expected on the basis. ஸோ இப்போ அட்டாமிக் ரேடியை வந்துட்டு சேமாக இருக்குன்ற காரணத்தினால நம்ம எக்ஸ்பெக்ட் பண்ணதை விட ரொம்பவே அதிகமான சிமிலாரிட்டிஸ் இஸ் ப்ரெசென்ட் இன் ஃபிசிக்கல் அண்ட் கெமிக்கல் ப்ராப்பர்ட்டிஸ் ஆஸ் வெல். நாட் ஓன்லி த அட்டாமிக் ரேடியை, இட் இஸ் டர்னிங் அவுட் தட் டியூ டு திஸ் பர்டிகுலர் ரீசன் த ஃபிசிக்கல் அண்ட் கெமிக்கல் ப்ராப்பர்ட்டிஸ் ஆர் ஆல்சோ டர்னிங் அவுட் டு பி பிகமிங் த சேம். The factor responsible for the length and contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause. That is, the imperfect shielding of one electron by another in the same set of orbitals. அதாவது length and contractionக்கு ஒரு முக்கியமான ரீசன் என்ன அப்படின்னா the imperfect shielding, அதாவது சேம் செட் ஆஃப் ஆர்பிட்டல்ஸில் இம்பர்ஃபெக்ட் ஷீல்டிங் இருக்குன்றத ஒரு காரணம் அப்படின்ற சொல்கிறாங்க. ஸோ however the shielding of one 4f by another is less than that of one d electron by another, and as the nuclear charge increases along the series there is fairly regular decrease. ஸோ பேசிக்கலி என்ன நடக்குது, இந்த இம்பர்ஃபெக்ட் ஷீல்டிங்கின் காரணமாக அண்ட் ஷீல்டிங் எஃபெக்ட் ஆஃப் 4f எலக்ட்ரானோடைய ஷீல்டிங் அப்படின்றது இட் இஸ் பிகமிங் லெஸ்ஸர், அண்ட் இந்த பர்டிகுலர் இட் இஸ் லெஸ் தேன் தட் ஆஃப் ஒன் டி எலக்ட்ரான் பை அனதர் ஆஸ் வெல். ஸோ இந்த பர்டிகுலர் ரீசன்னால் நியூக்ளியஸோடைய சார்ஜ் அதிகமாக அண்ட் த இம்பர்ஃபெக்ட் ஷீல்டிங்கும் நடக்கிறன் காரணமாக த ரேடியஸ் இஸ் பிகமிங் drastically reduced. Okay, so the decrease in the metallic radius coupled with the increase in the atomic mass results in a general increase in the density. So radius decrease ஆகுது and mass increase ஆகுது அப்படின்னா obviously the density is going to decrease, which means that from titanium to copper the significant increase in the density may be noted. So இங்கே வந்துட்டு we have been given with a lot of, the one important physical properties, right? So atomic number, the electronic configuration, enthalpy of atomization, ionization enthalpy, metallic ionic radii in picometers, standard electropotentials and densities are given. So as you can see, the densities are increasing. Yes, that's fine, and we have seen atomic numbers, this is done, and we have seen the configurations as well, this is done as well. Now we will move down and we have seen the metallic or ionic radii depending upon their value. Okay, we have seen the metallic radii, right? Now we will talk about the ionization enthalpies. Yes, so why do transition element exhibit higher enthalpies of atomization? Because a large number of unpaired electrons in their atoms, they have stronger interatomic interaction, and hence stronger bonding between atoms results in the higher enthalpies of atomization. So basically unpaired electrons ஓட presence அதிகமாக இருக்கிறனால interatomic attractionும் அதிகமாக இருக்கிறது, interatomic bonding அப்படின்றது it is more favored அப்படின்ற காரணத்தினால it is having a higher enthalpy of atomization. ஓகே, இப்போ வந்துட்டு ஏன் இந்த பர்டிகுலர் 3D சீரீஸை பொறுத்த வரைக்கும் zinc is having the lowest enthalpy of atomization அப்படின்னா the reason is attributed to that zinc has completely filled electrons in its d and s orbitals, which means that it has attained the pseudo-inert gas configuration. Pseudo-inert gas configuration இருந்தா which means that it is not gonna form any bond with any other type of elements. அப்போ easily it can be like broken down அப்படின்றது. அதாவது இப்போ மற்ற எலிமெண்ட்ஸ் எல்லாம் பார்த்தீங்கன்னா லைக் ஸ்காண்டியம் டு காப்பரை பொறுத்த வரைக்கும் ஃபர்ஸ்ட் ஆஃப் ஆல் we will have to do atomize them. They will be present in terms of groups or in compounds. ஆனால் இந்த பர்டிகுலர் ஜிங்கை பொறுத்த வரைக்கும் இட்ஸ் நாட் கோன் பி present in compounds, and if at all if it is present in there, it's going to be unstable, and if I'm giving slightly more just more energy, then obviously I can obtain I will be able to atomize that particular zinc atom, hence it is having the lowest enthalpy, that due to the fact that it has no unpaired electron leading to its decrease in the interatomic interactions. That's the reason. Entering into ionization enthalpies, there is an increase in the ionization enthalpy along each series of transition elements from left to right due to an increase in nuclear charge, which accompanies the filling of the inner d orbitals. Table 8.2 gives the values of the first 3 ionization enthalpies of the first series of transition elements. These values show that the successive enthalpies of these elements do not increase as deeply as in the case of non-transition elements. The variation in ionization enthalpy along a series is much less in comparison to variation along a period. அதாவது ஒரு சீரீஸில் நம்மளோட வேரியேஷனை கம்பேர் பண்ணும்பொழுது பீரியடில் இருக்க கம்பேரிஷனோட இட்ஸ் கோன் பி லெஸ்ன்றதை சொல்கிறாங்க. இட்ஸ் நாட் கோன் பி அ கிரேட்டர் இன்க்ரீஸ் இன் த என்தால்பிஸ் அப்படின்றத மென்ஷன் பண்ணுறாங்க. த ஃபர்ஸ்ட் அயனைசேஷன் என்தால்பி இன்க்ரீசஸ், பட் த மேக்னிடியூட் ஆஃப் இன்க்ரீஸ் இன் த செகண்ட் அண்ட் தேர்ட் இஸ் மச் ஹையர் அலாங் அ சீரீஸ். அதாவது ஒரு சீரீஸில் இட்ஸ் கோயின் டு பி ஹையர் ஃபார் தேர்ட் அண்ட் செகண்ட் அண்ட் தேர்ட் அயனைசேஷன் என்தால்பி அப்படின்றத சொல்ல வராங்க. Okay, fine. The irregular trend in the first ionization enthalpy of the metals of the 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. The irregular trend in the first ionization enthalpy of the metals of the 3D series, though of little chemical significance, can be accounted for the considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. You have learned that when d block elements form ions, ns electrons are lost before n minus 1d electrons. As we move along the period in 3D series, we see that the nuclear charge increases, but the electrons are added to the orbital of inner subshell. These 3D electrons shield the 4f electron from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield another. Therefore, the atomic radii decreases less rapidly. Thus, the ionization energies increase only slightly along the 3D series. The doubly or more highly charged ions have dn configurations with no 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases because one d electron does not shield another from the influence of the nuclear charge because d orbitals differ in direction. However, the trend of steady increase in the second and third ionization breaks for the formation of Mn2 plus and Fe3 plus respectively. So basically என்ன சொல்ல வராங்க அப்படின்னா there is an irregular trend in the increase of first ionization enthalpy. அதாவது இதுக்கான காரணம் வந்துட்டு first is attributed towards the removal of one electron. ஒரு எலக்ட்ரானை ரிமூவ் பண்ணிட்டோம் அப்படின்னா obviously the relative energies will be altered for 3s and 3s and 4d series ஓட energies are altered அப்படின்ற சொல்கிறாங்க. Energies are altered, yes. So basically என்ன சொல்ல வராங்க, as we increase, as the atomic number increases, the electrons are actually added towards the 3D series, and whenever I'm removing an electron, I'm removing an electron from the 4s series. So if I'm actually adding an electron towards the 3D series, then it's effectively shielding me against my removal from the atom because the effective nuclear charge is decreased due to an addition in the inner orbital, which means that removal of an electron from the outermost orbital is not going to be that difficult. Hence, on the particular reason காரணமாக the increase in ionization enthalpy is also not going to be that effective அப்படின்றத சொல்கிறாங்க. A general trend of increasing values of second ionization enthalpy is expected as effective nuclear charge increases. So by effective nuclear charge வந்துட்டு second ionization enthalpyலேருந்து it's going to increase. ஏன்னா ஒரு d electron இன்னொரு d electron வந்துட்டு ஷீல்ட் பண்ண போகிறது it's not going to be that effective. So it's going to be increasing and it's going to have that general trend. So the trend of steady increase in the second and third ionization enthalpy breaks for the formation of Mn2 plus, where we'll obtain 3d5. 3d5 there will be a steady increase until I'm obtaining 3d5 configuration. There will be a steady increase. As soon as I obtain that, then this increase is going to be drastic because it is having a half-filled configuration, which means that it's going to be more stable. To remove an electron from a more stable configuration requires a lot more energy, and similar will be the case of third ionization enthalpy. Third ionization enthalpy, if I'm reaching from Fe3 plus, if I'm reaching 4s2 and if I'm removing the 4s2 electrons and the 3d6 on the one electron, then it is obtaining 3d5 configuration, and அங்கேருந்து remove பண்ணுறது will be much more difficult. So in both the cases, the ions have dv5 configuration. Similar breaks occur at corresponding elements in later transition series. So later transition seriesலையும் manganese கீழே இருக்கிற elementsக்கும் Fe கீழே இருக்கிற elementsக்கும் will have similar breaks அப்படின்ட்டு சொல்கிறாங்க. So in the interpretation of variation in ionization enthalpy for an electronic configuration dn is as follows. So basically variation என்ன நடக்க போகுது, dn configuration இருந்தால் the three terms responsible for the value of ionization enthalpy are attraction of electron towards the atom, repulsion between the electrons and the exchange energy. So இந்த மூணு பேசிஸில் தான் வந்துட்டு we will talk about ionization enthalpy. Attraction of electrons, exchange energy, repulsion between the electrons. Exchange energy is responsible for the stabilization of energy state. ஒரு கொடுக்கப்பட்ட எனர்ஜி ஸ்டேட் வந்து ஸ்டேபிளாக இருக்கிறதுக்கு முக்கியமான காரணம் அந்த எக்ஸ்சேஞ்ச் எனர்ஜி அப்படின்றது தான். இட் இஸ் அப்ராக்சிமேட்லி ப்ரொபோர்ஷனல் டு த டோட்டல் நம்பர் ஆஃப் பாசிபிள் பேர்ஸ் ஆஃப் பேரல் ஸ்பின்ஸ் இன் த டீஜெனரேட் ஆர்பிட்டல்ஸ். ஸோ எத்தனை பேரல் ஸ்பின்ஸ் இருக்கோ அதுக்கு ப்ரொபோர்ஷனலாக இருக்கிறது தான் இட்ஸ் கோயிங் டு பி த எனர்ஜி ஸ்டேட்ன்ற சொல்கிறாங்க இந்த டீஜெனரேட் ஆர்பிட்டல்ஸ்னு சொல்கிறாங்க. And several electrons occupy a set of degenerate orbitals. The lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins, the Hund's rule. The loss of exchange energy increases the stability. Okay, when several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital in parallel spins. The loss of exchange energy increases the stability. பேசிக்லி ஹன்ஸ் ரூலில் வந்து என்ன சொல்கிறாங்கன்னா, நிறைய எலக்ட்ரான்ஸ் வந்து ஒரு டீஜெனரேட் ஆர்பிட்டாவில் ஃபில் பண்ணுது அப்படின்னா லோவஸ்ட் எனர்ஜி ஸ்டேட் என்னவாக இருக்கும்னா மேக்ஸிமம் நம்பர் ஆஃப் பேரல் ஸ்பின்ஸ் வந்துட்டு எந்த பர்டிகுலர் ஸ்டேட் கொடுக்குதோ, அதாவது if I have 5 electrons to be filled in a d5 configuration, this will be the most stable state where I will have maximum number of parallel spins 1 2 3 4 5. So that's what Hunt's rule states. ஸோ இந்த மேக்ஸிமம் நம்பர் ஆஃப் பேரல் ஸ்பின்ஸ் எவ்வளோ இருக்கும் அதுக்கு டைரக்ட்லி ப்ரொபோர்ஷனல் வில் பி த எக்ஸ்சேஞ்ச் எனர்ஜி. அண்ட் எக்ஸ்சேஞ்ச் எனர்ஜி இந்த பர்டிகுலர் கேஸில் இட் வில் பி ஹையராக இருந்தால் ஸ்டெபிலிட்டி வில் பி லோவர். ஸோ பேசிக்கலி லாஸ் ஆஃப் எக்ஸ்சேஞ்ச் எனர்ஜி டென்ஸ் டுவர்ட்ஸ் த இன்க்ரீசிங் ஆஃப் ஸ்டெபிலிட்டி. ஸோ ஆஸ் த ஸ்டெபிலிட்டி இன்க்ரீசஸ் த அயனைசேஷன் பிகம்ஸ் மோர் டிஃபிகல்ட். ஸோ இப்போ எக்ஸ்சேஞ்ச் எனர்ஜி கம்மியாகும் பொழுது, அதாவது பேரிங் அப் நடக்கும் பொழுது, அப்போது we'll have stable configuration. Stable configuration to the ionization பண்ணுறது கஷ்டம். There's no loss of exchange energy at D6 configuration. இப்போ D6 configuration பொறுத்த வரைக்கும் there should be no loss of exchange energy. ஏன் அப்படின்னா basically it is forming this more amount of so Mn plus has 3d5 4s1 configuration, and configuration of Cr plus is 3d5. Therefore ionization enthalpy of manganese is lower than chromium. இப்போ chromium plus உடைய configuration வந்து 3d5. இப்போ இந்த 3d5ல ஒரு எலக்ட்ரான் ரிமூவ் பண்ணுறதுக்கும் manganese plus is 4s1 3d5. 4s1 3d5ல இருந்து 4s1 electron remove பண்ணுறது is going to be relatively easier. So the enthalpy is going to be lesser for manganese than that of chromium. Yes. In the same way Fe2 plus has d6 configuration and M2 plus has d5 configuration. So it's going to be the ionization enthalpy of Fe2 plus is lower than manganese. In other words, we can say that the third ionization enthalpy of iron is lower than that of the manganese. So the lowest common oxidation state of these metals is 2. So the lowest common oxidation state, it will generally give up 2 electrons, okay, at any cost. From the gaseous atoms, it forms M2 plus ion. To form the M2 plus ions from the gaseous atoms, the sum of the first and second ionization enthalpy is required in addition to the enthalpy of atomization. So first atomization பண்ணதுக்கு அப்புறம் for making it an M2 plus ion, we will require the first and second ionization enthalpies. The dominant term is the second ionization enthalpy, which shows unusually high values for chromium and copper. So chromium and copper, the amount of energy which will be you will have to give as an input for making them atomize and form an M2 plus ion will be dominated by the second ionization enthalpy, as chromium and copper will have D5 and D10 configurations respectively at this particular moment. So the value for zinc is the value for zinc is correspondingly low, as the ionization causes the removal of one 4s electron, which results in the formation of a stable D10. The trend in the third ionization enthalpy is not complicated by the 4s orbital factor and shows greater difficulty of removing an electron from the D5 and D10. ஸோ அதாவது இந்த தேர்ட் அயனைசேஷன் என்தால்பியை பொறுத்த வரைக்கும் 4s பற்றி யோசிக்கவே வேணாம். ஏன்னா 4sல கண்டிப்பாக எலக்ட்ரான்ஸே இருக்க போகிறது கிடையாது. ஸோ அப்போது இட் இஸ் கோயிங் டு கம்ப்ளீட்லி டிபெண்ட் அப்பான் half filled or completely filled stable state of D orbitals only. So the trend in third ionization enthalpies is not complicated by the 4s orbital factor. In general, the third ionization enthalpies are quite high. Also, the high values for the third ionization enthalpies of copper, nickel and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. So copper, nickel, zinc third ionization enthalpy அதிகமாக இருக்கிறனால ஜென்ரலாக they will not show these particular oxidation states, higher oxidation states than 2. So although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. அதாவது பேசிக்கலி இந்த ரிலேட்டிவ் ஸ்டேபிள் ஸ்டேட்டு, இந்த எக்ஸ்சேஞ்ச் எனர்ஜி, இந்த பேசிஸ்லாம் பார்க்கும்பொழுது இட் லுக்ஸ் ஃபைனாக இருந்தாலும் வி கேனாட் கிவ் அ ஜென்ரல் எக்ஸ்பிரஷன் அப்படின்றதான் சொல்ல வராங்க ஃபைனலாக. மூவிங் டவுன் த ஆக்சிடேஷன் ஸ்டேட்ஸ், ஒன் ஆஃப் த நோட்டபிள் ஃபீச்சர்ஸ் ஆஃப் த டிரான்சிஷன் எலிமெண்ட்ஸ் இஸ் த கிரேட் வெரைட்டி ஆஃப் த ஆக்சிடேஷன் ஸ்டேட்ஸ் தீஸ் மே ஷோ இன் தேர் காம்பவுண்ட்ஸ். டேபிள் 8.3 ஷோஸ் த காமன் ஆக்சிடேஷன் ஸ்டேட்ஸ். அதாவது ஸ்கேண்டியமில் இருந்து மெங்கனீஸ் வரைக்கும் வில் ஹாவ் ஆக்சிடேஷன் ஸ்டேட்ஸ் வேரிங் ஃப்ரம் +2 to +7, அண்ட் அதிலிருந்து இட் இஸ் கோனா டிக்ரீஸ் ஃப்ரம் +6 to +2. அண்ட் ஃபைனலாக இருக்க அந்த நிக்கல் காப்பர் இவனுக்குலாம் வந்துட்டு மோஸ்ட் காமன் ஆக்சிடேஷன் ஸ்டேட்டே அந்த +2 அது மட்டும்தான். Ferrum cobalt we will have +2 +3 oxidation state as common and yes. Moving down, the elements that give the greatest number of oxidation states occur in or near the middle of the series. அதாவது in general for the d orbital or d block elements and the element showing the greatest number of oxidation states only it will occur at the middle or in near middle. Like in case of the 3D series we have manganese which shows up from +2 to +7 oxidation state. The lesser the number of oxidation states at the extreme ends stems for either too few electrons to share or too many electrons for higher valence. Okay, thus early in the series scandium 2 is virtually unknown and scandium 4 is more stable than for titanium 4 is more stable than titanium 3 or titanium 2. Okay, at the other end the only oxidation state of zinc is +2 where no d electrons are involved. The maximum oxidation states of reasonable stability correspond to the value to the sum of the s and d electrons up to manganese. அதாவது மேக்ஸிமம் ஆக்சிடேஷன் ஸ்டேட் ஆஃப் ரீசனபிள் ஸ்டெபிலிட்டி அப்படின்றது அப் டு மேங்கனீஸ் வந்துட்டு இட் இஸ் த சம் ஆஃப் எஸ் அண்ட் டி எலக்ட்ரான்ஸ். ஃபார் எக்ஸாம்பிள் லெட்ஸ் டாக் அபவுட் ஃப்ரம் ஸ்காண்டியம், டைட்டானியம், வெனாடியம், குரோமியம் அண்ட் மேங்கனீஸ். ஸோ வில் ஹாவ் 2 1 2 2 2 3 2 4 2 5. So this is the SD SD SD. This is actually 1 5 SD and SD. So basically the maximum stable oxidation state only it's going to be s orbital electrons and p orbital electrons up to manganese, that's +3 +4 +5 +6 +7. Yes, so like titanium 4, yeah, vanadium 5, chromium 6, manganese 7, followed by rather abrupt decrease in the stability of higher oxidation states. So higher oxidation state will be very very unstable for higher elements. So that the typical species to follow are Fe2, Fe3, cobalt 2, 3, nickel 2, copper 1, 2 and zinc 2. So that for iron the common oxidation state is 2, 3. For cobalt it's going to be 2, 3. For nickel it's going to be 2, and for copper it's going to be 1 or 2, and for zinc it's going to be 2. So that's going to be the higher oxidation states will become unstable as we go from the middle towards the near end. So the variability of oxidation states, a characteristic of transition elements, arises out of incomplete filling of d orbitals. ஓகே, ஸோ வேரியபிலிட்டி ஆஃப் ஆக்சிடேஷன் ஸ்டேட்டோட காரணம் இப்போ வந்துட்டு நம்ம இந்த ஆக்சிடேஷன் ஸ்டேட் வேரியேஷன்லாம் என்னென்னு பார்த்துட்டோம். இதுக்கான காரணம் காஸ் என்னன்றது பார்க்குறோம். இட் இஸ் டியூ டு த இன்கம்ப்ளீட் ஃபில்லிங் ஆஃப் d orbitals in such a way that their oxidation states differ from each other by unity. So in contrast with the variability of oxidation state of non-transition elements where the oxidation state normally differ by unit of 2. So non-transition elements பொறுத்த வரைக்கும் oxidation state if it is +1 அப்படின்னா the next common oxidation state will be +3. But in case of this particular guys it's going to be +1 and +2. The difference between the oxidation state will be only unity. So an interesting feature in the variability of oxidation states of the d block elements is noticed among the groups 4 through 10. Although in the p block the lower oxidation states are favored by the heavier members due to the inert pair effect. Opposite is true in groups of d block. அதாவது d block பொறுத்த வரைக்கும் என்ன சொல்ல வராங்க அப்படின்னா, ஓகே p blockல லோவர் ஆக்சிடேஷன் ஸ்டேட் வந்து ஹெவியர் மெம்பர்ஸ்லாம் வந்துட்டு உதவி செய்வாங்க அப்படின்ற பொழுது d block பொறுத்த வரைக்கும் ஹையர் ஆக்சிடேஷன் ஸ்டேட்ஸ் ஆர் ஃபேவர்ட் பை ஹெவியர் மெம்பர்ஸ்ன்ற மாதிரியான ஒரு விஷயத்தை சொல்ல வராங்க. ஓகே ஃபைன். ஃபார் எக்ஸாம்பிள் இன் குரூப் 6, ஸோ குரூப் 6ல we'll have molybdenum 6 and we'll have wolfram 6. So these are 4D and 5D series elements, and these guys are more stable. Stability பொறுத்த வரைக்கும் the higher member is basically contributing for more stability than chromium 6 ன்னு சொல்றாங்க. So in a group the higher oxidation the higher elements will stabilize the higher oxidation states ன்னு சொல்றாங்க. So chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas molybdenum oxide or wolfram oxide are not. ஏன் அப்படின்னா strong oxidizing agent ஏன் அப்படின்னா it gets reduced. Okay, in acidic medium chromium 6 is in the form of, okay, which means that basically chromium dichromate la basically chromium will be in +6 oxidation state, and +6 oxidation state proves to be less stable. It's a strong oxidizing agent அப்படின்னா ஏன் அப்படின்னா it cannot hold more of positive charge for a longer time. which means that it will definitely need electrons and it needs readily, and that's why it is turning out to be more more an oxidizing agent. It's turning out to be a strong oxidizing agent. Moving down, low oxidation states are found when a complex compound has ligands capable of pi acceptor character in addition to the sigma bonding. ஸோ அதாவது லோ ஆக்சிடேஷன் ஸ்டேட் வந்துட்டு எப்போ பார்ப்போம் அப்படின்னா இன் காம்ப்ளெக்ஸ் காம்பவுண்ட்ஸில், அதாவது லைகேண்ட்ஸ் வந்து if it has a pi accepting character in addition to the sigma bond, then we'll obtain the low oxidation states. In case of nickel, ferrum, in which there is a pi accepting character, அப்போது கண்டிப்பாக there's going to be the oxidation state is going to be 0, which is the lowest. It's actually not favored, but it is found in case of complex compounds. Okay, which of the 3D series of transition elements exhibits the largest number of oxidation in Y? Manganese ஏன்னா there are a lot of unpaired electrons present. Unpaired electrons அதிகமாக இருக்க more the number of unpaired electrons, more will be the variation in oxidation state அப்படின்றத சொல்கிறோம். So now we are entering into quite a difficult part of this particular chapter, that's trends. We'll have to remember them. So trends in the let me just have So moving down, we'll talk about the trends in turning M2 plus ion cation to metal. So the table, okay, related to the transformation of solid metal atoms to M2 plus ions in solution and their standard electrode potentials. The observed values of the standard electrode potential and those calculated using the data of the table 8.4 are compared in the figure 8.4. So basically we'll have a kind of observed value and the calculated potential value to liberate H2 from acids. அதுக்கான அர்த்தம் என்னன்னா, it is not a very good base. It is not a very good base அப்படின்னா என்ன அர்த்தம்? M2 plus it means that its inability to abstract H2, okay, abstract H2 from acids அப்படின்னா basically என்னது reduction potential னா என்னது, higher the reduction potential more will be its value. Okay, wait a minute, reduction potential அதிகமாக இருந்தால் யூடியூப் சேனல் வேற என்ன, #restart அரமணி.
யாருமே நான் கமெண்ட்டும் பண்ணல, ஒன் வாட்சிங் தான்.
நீ தானே?
நான் ஒருத்தன் தான்.
ஸோ
1 likes 1 views.
யார் லைக்?
ஆமாம்,
பர்த்டே. ஓகே,
யாருமே நான் பார்க்கலடா.
பார்க்க மாட்டாங்கடா யாருமே. போடுறது மட்டும் தான் நம்ம வேலை. Okay, so moving on, we are talking about the trends in converting a dye-positive cation into a metal of a neutral charged part. So basically, as we have seen the electrode potential values, the electrode potential value or calculated மற்றும் observed values பார்க்கும்போது, one thing that stands out from all the other metals is copper. So copper ஓட electrode potential value, that is standard electrode potential value, is positive. Standard electrode potential value shows the reduction potential, and if the reduction potential is positive, means that it has an ability to abstract electrons more, which means that it has an inability to abstract protons. Aதாவது it has inability to abstract H2 from acids. That's what they're trying to say over here. The unique behavior of copper having a positive electrode potential accounts for its inability to liberate H2 from acids. So basically it cannot liberate H plus ion from an acid. Only oxidizing acids such as nitric and hot concentrated sulfuric acids react with copper. ஏன் அப்படின்னா basically this guy gets reduced. I mean like, okay, react with copper, the acids being reduced. Yes, actually yes, these guys are getting reduced. The high energy to transform copper to copper 2 plus is not balanced by its hydration enthalpy. The general trend towards less negative electrode potential values series is related to the general increase in the sum of first and second ionization enthalpies. So basically, turning a copper solid into a copper it requires a lot of energy. Ionization enthalpy or sum வச்சு பார்க்கும் பொழுது we can see that there are lesser electron potential values, which means that they have an ability to get off value of manganese. To note that the value of the electron for manganese, nickel and zinc are more negative than expected. So that the manganese, it is expected to increase, but unfortunately it is turning out to have a lesser electrode potential value than expected, and similarly for nickel and cobalt as well, cobalt and nickel as well. So that's the conversion of dye positive cation into a neutral atom. Moving on. Okay, why is copper 2 plus is reducing and manganese 3 plus is oxidizing when both have a D4 configuration? Okay, fine. So copper 2 plus is reducing as its configuration changes from D4 to D3. அதாவது reduce ஆகிறது மூலியமா it is converted to D4 to, okay, if at all, if I'm trying to remove the latter having a half fill T2G level. Okay, basically copper 2 plus is reducing until it is getting oxidized, implies it is giving up an electron. Upon giving an electron, it is obtaining a D3 configuration, and in terms of T2G level, we'll say that this guy is having a half filled T2G level. On the other hand, the change with Mn3 plus to Mn2 plus results in the half filled configuration of D5, which means that there is going to be an extra stability. Moving down, the electrode potential value, that is from turning a dye positive cation into a neutral metal atom for copper, is positive. What is the possible reason? So it is having a higher when, okay, it requires a higher energy for transforming it from a copper to copper 2 plus ion, whereas the only other factor which can hydrolyze or counterattack this is the hydration enthalpy. And if this hydration enthalpy is lesser, then obviously it's gonna have a positive electrode potential value. Okay, we have certain thermochemical data for the first two transition elements for reduction of M2 plus to M. Okay, I'm not gonna enter into this now. Now let's talk about trends in turning a tri-positive cation into a di-positive cation, which means that reduction potential. An examination of the electrode potential value shows the varying trends. The low value of scandium reflects that the scandium 3 plus, which has a noble gas configuration. So noble gas configuration, adding up an electron, it doesn't matter, I think. The highest value for zinc is due to the removal of an electron from the stable D10 configuration. Okay, I think it's addition of electron, right? Okay, the highest value for zinc is due to the removal of electron from a stable D10 configuration. D10 configuration, if at all, if I'm trying to remove an electron, then obviously it will require more amount of energy. The comparatively high value for manganese shows that it is basically D5 configuration, and if I'm trying to remove an electron from D5 configuration, then obviously its stability will be interrupted, which means more amount of energy will be required for interrupting its stability. As comparatively low value for ferrum shows the extra stability of Fe3 plus. Fe3 plus ஓட வேல்யூ வந்துட்டு லைக் ஃபார்மேஷனுக்கு இட் ரெக்வயர்ஸ் ஒன்லி அ லெஸர் அமௌண்ட் ஆஃப் எனர்ஜி. ஏன் அப்படின்னா it's actually obtaining D5 configuration, which is half filled configuration. The comparatively low value for vanadium is relatively related to the stability of V2 plus. So vanadium k want comparatively low value abdina, we can talk about T2G set. So for ferrum we'll be having a half filled configuration. For zinc there will be higher value due to the fact of D10 configuration and removal of an electron from D10 configuration, and the higher value for manganese 2 plus as well, and the lower value for states. So table 8.5 shows the stable halides of the 3D series of the transition metals. The highest oxidation numbers are achieved in TiX4, that is the tetra halides, VF5CrF6. So the highest oxidation state. So titanium is having a higher oxidation state of +4, maximum oxidation state of +4, and for vanadium it's +5, and for chromium it's +6. Yes, the +7 state for manganese is not presented in simple halides but in MnO3F is known, and beyond manganese no metal has a trihalide. So manganese-க்கு மேல எந்த ஒரு மெட்டலுக்கும் வந்து trihalide இல்லை except that of ferrum and cobalt. Ferrum and cobalt வரைக்கும் தான் we'll have trihalides, and trihalides which means that it shows a +3 oxidation state அப்படின்றத சொல்ல வராங்க. And after cobalt we do not have +3 oxidation state, a stable +3 oxidation state அப்படின்றத தான் சொல்ல வராங்க. And the ability of fluorine to stabilize the highest oxidation state is due to the either higher lattice energy as in the case of cobalt fluoride, or higher bond enthalpy terms for the higher covalent compounds. Okay, so why is it able to stabilize the higher oxidation state? ஏன்னா higher oxidation stateல it is basically due to the higher lattice energy. So lattice energy அப்படின்றது in case of cobalt fluoride it requires more amount of lattice energy for its survival, and it is provided by fluorine. The higher bond enthalpy for higher covalent compounds. அதாவது higher covalent compoundsல it will be having higher bond enthalpy. Higher bond enthalpy means more stable compound. Yes, so the ability is due to but there can be a question that why is that fluorine is able to stabilize the highest oxidation state? It's due to the fact that it can either be due to their higher lattice energy in case of cobalt fluoride, or higher bond enthalpy for higher value covalent compounds such as VF5 or CrF6. Also V5 plus 5 is represented only by VF5. The other halides however undergo hydrolysis to give oxo halides such as VOX3. அதாவது V5 plus அதாவது 5 plus oxidation state shown by vanadium, it is represented only by VF5 and not by VCl5 or VBr5. The other halides however undergoes hydrolysis to give oxo halides. Mata halides such as VF4, VF3 or like VBr3, VBr4 இதெல்லாமே வந்துட்டு it can go hydrolysis. The another is there in instability in the low oxidation state. So it is unstable in lower oxidation states, and it's more stable in the higher oxidation state due to the higher lattice energy or due to the higher bond enthalpy for the higher covalent compounds. Yes, moving down, and the same applies to CuX. So the CuX it will be able to, okay, fine. On the other hand, all copper 2 halides are known except at iodide. அதாவது copper 2 halides such as CuF2, CuCl2, CuBr2 இந்த மாதிரி நிறைய விஷயங்கள் தெரியும். Though CuF2 is unstable, it's fine, but it is present there. And copper 2 halides எல்லாமே தெரியும் except that of iodide. Okay, copper 2 halides are all known except that of iodide. In case of copper 2 plus என்ன நடக்கும் அப்படின்னா I minus it is oxidizing to I2 அப்படின்ற சொல்கிறாங்க. So let's say if I have copper 2 plus upon reaction with iodine, it should form Cu2I2, but it is actually turning out to convert the I minus 2 and stabler, that is having a zero oxidation state, right? So however, many copper 1 compounds are unstable in aqueous solution and undergoes disproportionation. So plus 1 oxidation state like copper compounds, right, it will undergo disproportionated, leading to the reduction in oxidation occurring at the same time. So the stability of copper 2 plus rather than the copper plus is due to the much more negative hydration enthalpy of copper 2 plus aqueous than that of copper plus, which more than compensates for the second ionization enthalpy. அதாவது காப்பர் ப்ளஸ் வந்துட்டு ஒய் இட் இஸ் அன்ஸ்டேபிள் அப்படின்னா காப்பர் 2 தேன் காப்பர் 2 ப்ளஸ் காப்பர் 2 ப்ளஸில் அப்டைன் ஆகிற அந்த பர்டிகுலர் ஹைட்ரேஷன் என்தால்பி அப்படின்றது இட் இஸ் மச் ஹையர் தேன் த செகண்ட் அயனைசேஷன் என்தால்பி, விச் மீன்ஸ் தட் இட் இஸ் ஸ்டெபிளைசிங் த காப்பர் 2 ப்ளஸ் மோர் ஈஸிலி அப்படின்றத சொல்ல வராங்க. Okay, we have seen about copper, we have seen the fluorides, why that fluoride are more stable at the higher oxidation states, and we have seen the trends in stability of oxidation states. Moving on, the highest oxidation state in the, okay, the ability of oxygen, now we will talk about oxygen. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. So as fluorines are the most electronegative elements, the second most electronegative element is oxygen, and hence it will also have the ability to stabilize the highest oxidation states. The higher oxidation numbers in the oxides coincides with the group numbers and is attained in scandium oxides to manganese Mn2O7. That we have seen in halides. In case of oxides பொறுத்த வரைக்கும் the highest oxidation number வந்துட்டு it is obtained with respect to the group number. See, for example, scandium 2O3, it is scandium will have a plus 3 oxidation state in this particular case, and then for manganese we will have plus 7 oxidation state in Mn2O7, right? So beyond group 7 no higher oxides of Fe above Fe2O3 are known. ஸோ அதாவது குரூப் 7க்கு மேலே போகும்பொழுது எஃப்இக்கு அபவ் Fe2O3க்கு மேலே எந்த ஒரு பர்டிகுலர் ஆக்சைட்ஸும் வந்து கிடையாது. although ferrates FeO4 minus with Fe4 plus oxidation state is also present in alkaline media, but they readily decompose to form Fe2O3 and dioxygen. Besides the oxides, oxocations stabilize the V5 and VO2 plus, V4 as VO2 plus, VO2 taken B, oxygen taken twice, whole plus charge, and vanadium 4 plus as VO with a whole 2 plus charge, and titanium 4 as TiO taken 2 plus charge. So அதாவது ஆக்சைட்ஸை தவிர்த்து, ஆக்சைட்ஸ் ஆர் பேசிக்கலி ஆக்சிஜன் இன் வேரியஸ் ஃபார்ம்ஸ். Oxocations will also be able to stabilize the whatever the thing is. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. அதாவது the ability for oxygen to stabilize the higher oxidation state will definitely exceed the fluorine அப்படின்றத சொல்ல வராங்க. எஸ், ஸோ இப்போ நம்ம பார்த்துருக்கோம் oxocations will also be able to stabilize அப்படின்றதையும் பார்க்குறோம். Oxides will also be able to stabilize the higher oxidation states. Thus the highest manganese fluoride is Mn4, whereas the highest oxide is Mn2O7. அதாவது though fluorides being stabilizing, though has the character of stabilizing a higher oxidation state, is only be able to form Mn4 plus, whereas in case of oxygen it is able to stabilize even Mn7 plus. So the ability of oxygen to form multiple bonds to metals explains its superiority. இதுக்கான காரணம் என்ன சொல்கிறாங்கன்னா, it has the ability to form multiple bonds to metals அப்படின்றத சொல்கிறாங்க. So in the covalent oxide manganese, okay, Mn2O7, each manganese is tetrahedrally surrounded by oxygens including a manganese oxygen manganese bridge. அதாவது கோவேலண்ட் ஆக்சைடில் such as manganeseல manganese is tetrahedrally surrounded அப்படின்றத சொல்கிறாங்க. The tetrahedral MO4N minus ions are known as vanadium 5, chromium 6, manganese 5, manganese 6 and manganese 7. Okay, so in the particular case வந்து it is not talking, I don't think they are talking about oxygen. So covalent oxide they are talking how manganese is being surrounded, it is having a manganese oxygen manganese bridge அப்படின்றத பற்றி பேசுகிறாங்க. The tetrahedral MO4 2 minus ions are known for vanadium 5, chromium 6, manganese 5, manganese 6 and manganese 7. So basically we are having certain oxides being given listed out in this particular table, right? Moving down, how would you account for the increasing oxidizing power in the VO2 plus Cr2 minus MnO4 minus? Okay, wait a minute. Okay. Manganese, this is due to the increasing stability of the lower species to which they are reduced. So the increase in oxidizing power means the oxidizing power is highest for MnO4 minus, where manganese is present in the oxidation state of plus 5. Now upon reducing, it gets reduced to convert, okay fine, convert to plus 2 oxidation state, I hope. Cr2O72 minus VO2 plus. Okay, so basically in the particular case பொறுத்த வரைக்கும் manganese will uh, get reduced to its particular plus 2 configuration, I think, if at all, if it has a higher oxidizing power. And similarly VO2 plus, in case of VO2 plus we have vanadium in 5 configuration, plus 5 configuration. Now that can be reduced to form a plus 2 stabler plus 3 or plus 2 configurations. Similarly chromium, which is in plus 6 configuration, I hope, will be reduced to a more stabler configuration அப்படின்றதா. And that's the reason. How do you account for the irregular variation of ionization enthalpies in the first series of transition elements? Okay, first series of transition elements la why do we have irregular variation of ionization enthalpies nu kekranga. Okay, first and second ionization enthalpies. So why do we have irregularity? It can be attributed towards hydration enthalpies. Okay, let me just show you the pages so that it will be better. The ionization enthalpies. So the variation in ionization enthalpy, basically it depends upon the exchange energy, stabilization, the electron repulsion, and the attraction between the electron and the nucleus. Okay, I mean they've asked a complete passage to explain, so I will have to explain for each and every element from its plus 1 to plus 2 oxidation states. I think everyone might know this, so I'm not getting into this now. Moving on, let's talk about the chemical reactivity and the electropotential values, standard electropotential values. So the transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is they are unaffected by single acids. அதாவது transition metals அப்படின்றது they vary widely in their chemical reactivity அப்படின்ற சொல்கிறாங்க. And many of them are sufficiently electropositive to dissolve in mineral acids அப்படின்ற சொல்கிறாங்க. Fine. And they are few of them are noble, that is they are unaffected by single acids. Okay, fine. So that's the first thing they are talking about, which means that bases, I mean like metals are basically bases as they can accept a pair of electrons or donate whatever, they can donate a pair of electron or accept a H plus ion, whatever. So the metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molarity of H plus. Okay, though the actual rate at which these metals react with oxidizing agents like hydrogen is sometimes slow. Okay, so for example, titanium and vanadium in practice are passive to dilute non-oxidizing acids at room temperature. The standard electropotential values for M2 plus to M, that is dipositive cation to a metal, indicate a decreasing tendency to form divalent cations across the series. This general trend towards the less negative electropotential values is related to the increase in the sum of the first and second ionization enthalpies. Okay. It's interesting to note that electropotential values for manganese, nickel, and zinc are more negative than expected from the general trend. Whereas the stabilities of half-filled D say for Mn2 plus is completely filled D10 in zinc are related to the electrode potential values. For nickel, electropotential values related to the highest negative enthalpy of hydration. So nickel currently we will have the highest negative enthalpy of hydration. For manganese we will have the plus D5 half-filled D5 subshell configuration, which means that for reducing it or for like the reduction potential will be least. Okay, whatever. Okay, so the metals of the first series except of copper, they react with or oxidized with H plus ion, though the actual rate is really slow for H plus. For titanium, vanadium in practice are passive to dilute non-oxidizing agents, acids. The electropotential values from M2 plus indicate a decreasing tendency to form divalent cations across the series. Decreasing tendency, okay, divalent cation or decreasing tendency சொல்றாங்க. Okay, the general trend towards the less negative electropotential values is related to the increase in the sum of first and second. Why is that? Because that there is an increase in the first and second ionization enthalpy as we go down, and there's interesting to note that the manganese, okay fine. So an examination of the electropotential standard electropotential values for the redox couple for tripositive to dipositive cation shows that the manganese 3 plus manganese tripositive cation and cobalt tripositive cations are the strongest oxidizing agents, which means they have the highest tendency of getting reduced. Mn3 plus manganese will have a configuration of okay in aqueous solutions. The ions titanium 2 plus, vanadium 2 plus are the strongest reducing agents, which means that they get oxidized and they will be able to liberate hydrogen. Reducing agents, okay, they will be able to from a dilute acid. Reducing agent, this guy gets oxidized. In the guy gets oxidized, there will be a removal of an electron. Yes, removal of an electron, or there will be basically a tendency towards accepting a proton. ஸோ டைட்டானியம் வெனாடியம் குரோமியம் இவங்க எல்லாருக்குமே வந்துட்டு their tendency reduces, which means that they get reduced as soon as they become tri I'm really sorry for the delay. So let's just get going. Yeah, let's get going. So let's talk about magnetic properties. So when a magnetic field is applied to substances, mainly two types of magnetic behavior are observed, that's diamagnetism and paramagnetism. Diamagnetic substances are repelled by the applied field, while paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. So diamagnetic it is repelling, paramagnetic attracting, very strongly attracting the ferromagnetic. Near the transition metals are paramagnetic which means get attracted. So paramagnetism arises due to the presence of an unpaired electron. The first series of transition metals, the contribution of orbital angular momentum is effectively quenched and hence no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using the spin-only formula of mu is equal to root of n into n plus 2, where n is the number of unpaired electrons and mu is the magnetic moment in units of Bohr magneton. So a single unpaired electron has a magnetic moment of 1.73 Bohr magnetons. A magnetic moment increases with the increasing number of unpaired electrons. Thus, the observed magnetic moment gives a full indication about the number of unpaired electrons present in the atom. The magnetic moments calculated from the spin-only formula and those derived experimentally from some ions of the first row transition element are given. The experimental data are mainly for the hydrated ions in solution or in the solid state. So as you can see, the calculated value and the observed value turns out really close. Yes, fine. So calculate the magnetic moment of a divalent ion in aqueous solution with atomic number is 25. With atomic number is 25, it's going to have 4s2 3d5, which means that if I'm removing 2 electrons, it's going to have 3d5 configuration, which means it has 5 unpaired electrons, which are 5 into 5, 7, that's a root 35 factor. It's about a 5.92 Bohr magneton. Moving down, calculate the spin-only magnetic moment of M2 plus aqueous ion. Okay, fine, I'm not going to get into this. So it's actually root of 3 into 5, root 15, it's about 3.92 or 3.93. Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. அதாவது என்ன amount of light வந்து frequency of light யூஸ் பண்ணுறோமோ அந்த amount of energy will be absorbed and it will get excited to a certain level. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light observed. The frequency of the light absorbed is determined by the nature of the ligand. அதாவது அந்த particular what frequency is obtained அப்படின்றது it depends upon the ligand nature. So in aqueous solutions where water molecules are the ligands, the colors of the ions observed are listed in table 8.8. A few colored solutions of the d block elements are illustrated. Okay, so as you can see, there are no unpaired electrons. No unpaired electrons, it's going to be colorless. And there are certain things to be noted, like Mn2 plus will be pink in color, and cobalt 2 plus, okay, wait, Fe2 plus will be green in color, and copper 2 plus will be blue in color. இதெல்லாம் வந்து சில முக்கியமான காம்பவுண்ட்ஸோட கலர்ஸ், இதெல்லாம் ஞாபகம் வச்சுக்கிட்டா பெட்டர். அண்ட் யா, இது மட்டும் தான் ஞாபகம் வச்சுருக்கேன். ஐ எம் நாட் கெட்டிங் இன்டு எனிதிங் ஃபர்தர். Next, formation of complex compounds. Complex compounds are those in which the metal ions bind a number of anions or neutral molecules, giving complex species with characteristic properties. அதாவது காம்ப்ளெக்ஸ் காம்பவுண்ட் அப்படின்னா என்னதுன்னா, basically the metal ions it will bind to a number of anions or neutral molecules, which gives rise to a complex species with characteristic properties. There are few examples such as FeCN taken 6 whole 3 minus, FeCN taken 6 whole 4 minus, CuNH3 taken 4 whole 2 plus, PtCl4 2 minus. The chemistry of complex compounds is dealt with. Okay, fine. The transition metals form a large number of complex compounds due to the comparatively smaller sizes of the metal ions, high ionic charges and availability of d orbital. ஏன் வந்து transition metals ஆல மட்டும் complex compound formation பண்ண முடியும் அப்படின்னா, it is due to the presence of a small size, higher oxidation state, higher ionic charges and availability of d orbitals. Okay, fine. Moving down, we will have catalytic properties. Transition metals and their compounds are known for their catalytic properties. The activities ascribed to their ability to adopt multiple oxidation states and to form complexes. Other than the transition metals have the ability to form multiple oxidation state and can form complexes, and due to this particular property they are being able to form compounds. So vanadium 5 oxide in contact process. So vanadium 5 oxide VO5, I think VO2 plus or something like that, is actually used in contact process. Yeah, it's VO2 plus. And finely divided iron is used in Haber's process, and nickel is used in catalytic hydrogenation. Catalysts at a solid surface involve the formation of bonds between the reactant molecules and the atoms of the surface of the catalyst. This has the effect of increasing the concentration of the reactants in the catalyst surface and also weakening the bonds in the reacting molecules. That is basically, okay, fine. The activation energy வந்து lower பண்றதுக்காகவும் and increasing the concentration of the reactants at the catalyst surface and the particular properties in Karamaha, we are using catalysts such as we are using catalysts. Also, because the transition metal ions can change their oxidation states, they become more effective as catalysts. அதாவது transition metal ions can change their oxidation state அப்படின்னா அப்போ கண்டிப்பாக they are very good fit for becoming catalyst. For example, we have iron 3 iron 3 which catalyzes the reaction between the iodide and persulfate ions. அதாவது if I have iron 3 ion, it is able to catalyze the reaction between iodide and persulfate ion. As you can see, this is 2I minus plus S2O8 2 minus. Yes, forms I2 with 2 sulfate. Yes, so it is mean in the particular reaction I'm gonna use iron 3 as a catalyst. So let me use Fe3 plus as a catalyst in this particular reaction. Now upon reaction with iodine, it leads to the formation of 2Fe2 plus iodine, that's complete iodine. Okay, then this 2Fe2 plus upon reaction with the 2 sulfate ion leads to the formation of S2O8 ion, OH 2 minus ion leads to the formation of 2 moles of sulfate ion. It basically breaks down the sulfate ion, yes, and forms Fe3 plus, which means that it is getting oxidized. Fe2 plus is acting as a reducing agent. It is reducing the S2O8 and forms 2 sulfate ions respectively, and it is getting oxidized to Fe3 plus. So this explanation Fe3 plus reacts with I minus, leads to the formation of iodine, and this and in this process it gets reduced to Fe2 plus. Now this Fe2 plus upon reaction with S2O8 reduces S2O8, leads to the formation of sulfate, and Fe3 plus is formed again. Moving on, formation of interstitial compounds. Interstitial compounds are those which are formed when small atoms like hydrogen, carbon or nitrogen, which are small in size, are trapped inside the crystal lattices of metals, and these are basically non-stoichiometric and are neither typically ionic or covalent. So basically they are not stoichiometric nor covalent nor ionic. So for example, we have titanium carbide, manganese nitrate, Fe3 taken H, okay, H, VHO, okay, 0.56 and okay, fine, great. So the formulas quoted do not of course correspond to any normal oxidation state of the metal. Because of the nature of their composition, these compounds are referred to as interstitial compounds. So basically these are not corresponding to their normal oxidation states, but they are referred to as their interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. So we will talk about the physical and chemical properties of these particular compounds. The first things first, they have high melting points. So in my interstitial compounds there will be high melting point. So in the questions கேட்க வாய்ப்பு இருக்கு. So state the properties of interstitial compounds. So first things first, we'll have to describe what an interstitial compound is. Basically these are compounds of non-stoichiometric, neither typically ionic nor covalent type of compounds, okay, which are formed when small atoms like hydrogen, carbon or nitrogen are trapped inside the crystal lattices. Okay, fine. So for example, we have titanium carbonate. Okay, the formulas quoted do not of course correspond to any The nature of their composition, these compounds are referred to as interstitial compounds. Okay, fine. The principal physical and chemical properties is that they have high melting points, higher than those of pure metals, and they are very hard. Yes, so they retain metallic conductivity, and they are chemically inert. So basically they are going to be hard, they have metallic conductivity, and they are going to be chemically inert, and they are going to have high melting points higher than the pure metals. Next, the alloy formation. An alloy is a blend of metals prepared by mixing the components. Alloys may be homogeneous solid solutions in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by the atoms with metallic radii that are within about 15% of each other. So basically in the particular alloys அப்படின்றது எப்படி ஃபார்ம் பண்ணுவோம் அப்படின்னா, it is formed by the atoms with metallic radii that are about 15% of each other. அதாவது 15% metallic radii வந்து ரெண்டும் சேமாக இருக்கும் பட்சத்தில் it will form an alloy அப்படின்னு சொல்கிறாங்க. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. அதாவது similar radii and characteristics எல்லாம் இருக்குன்னு காரணத்தினால alloys are readily formed by these metals. The alloys are so formed are hot. தெரியல 8:30. The alloys so formed are hard and have often high melting points. So basically the alloy formation அப்படின்றதுக்கு the metallic radii must be similar. Similar metallic radii means easier the alloy formed, and the alloys formed will be hard and they will have higher melting points as well. The best known are ferrous alloys. Ferrous alloys are chromium, vanadium, tungsten, molybdenum and manganese ore, used for the production of variety of steels and stainless steel. Ferrous alloys அப்படின்றது basically the combination of chromium, vanadium, tungsten, molybdenum, manganese. Okay, fine. Used for the production of variety of steels and stainless steels. Alloys of transition metals with non-transition metals such as brass, copper. Brass அப்படின்றது copper zinc alloy. Brass is copper zinc alloy. Yes. And bronze is copper tin alloy. ரெண்டையும் கன்ஃபியூஸ் பண்ணிடாதப்பா ராஜா. Brass oxidation state, basically when a particular oxidation state becomes less stable relative to the other oxidation states, one lower, one higher, it is said to undergo disproportionation. For example, we have manganese 6, it becomes unstable relative to manganese 7 and manganese 4 in acidic solution, which means that it gets converted, it gets oxidized and reduced simultaneously into plus 7 and so explain why copper plus ion is not stable in aqueous solutions. This is due to the fact that the hydration enthalpy obtained from the upon formation of copper plus is unable to contribute for its atomization energy and for its ionization enthalpy, and that's why it's not stable in its aqueous solution. Moving down, we have certain important compounds of transition element. Now this is the important part where we'll have to remember a lot. Yes, yeah. We are entering into the important part of the chapter. Now that's the oxides and oxo anions of metals. Let me just once check what they have asked till now. அந்த அறிவிப்போல் அன்பத்தருவாளே சின்ன அறிவிப்பும் இன்றி சுடுவாளே நீ தும்பிரடி ஆயுது ஊராகும் என்னோட உன்னோட பத்தி வச்சத்தார என் பார்வை உன்னோடு உம்பொம்மை கண்ணோடு பேசாம என்னோடு இறந்து போகோ காதாரோ. காம்பவுண்ட்ஸை பற்றி கேட்டரு கேளா தன்னனக்கா ஸ்ரீசம் வீரீசம் வத்சஸ்வராமே கோவிந்த கோவிந்த கோவிந்தநேசம் விடனாயி புத்திரம் ஸ்ரீ வெங்கடேஷம் கோவிந்தா கோபாலா கோவிந்த கோவிந்த பால பால. Chromium Cr2O3. Yes, that is it. M2O7. அந்த அறிவிப்போல் அன்பத்தருவாளே சின்ன அறிவிப்பும் நன்றி சுடுவாளே நீ தும்பி ஆயுசு நூறா. Okay, we have a question. Preparation of KMnO4. When MnO2 is fused with KOH in presence of KNO3, it gives a dark green compound. Okay, P2 plus reaction with MnO4 minus and H plus. Orange color of Cr2O7 2 minus ion changes to yellow when treated with alkali. When chromate over FeCr2O4 is fused with NaOH in presence of fat. Okay, we have questions. Yes, we have questions. Definitely we have questions based directly upon the equations that has been given. And then we have long answer questions. Only few questions have been available. I think that's fine actually. But Kandipa is having importance. I'm sorry, my mistake. அந்த அறிவிப்போல் அன்பத்தருவாளே சின்ன அறிவிப்பும் இன்றி சுடுவாளே நீ தும்பிரடி ஆயுசு நூறாக என்னுயிர் உன்னோட பத்திரச்சத்தார. So some important compounds of transition elements, oxides and oxo anions of metals. These oxides are generally formed by the reaction of metals with oxygen at higher temperature. அதாவது oxides are generally formed by the reaction of metals with oxygen at higher temperature. So all the metals except scandium form MO oxides which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained by in scandium 2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Besides the oxides, the oxocations will also be able to stabilize, such as V5, where V and plus 5 oxidation state is present in VO2 plus, V and plus 4 oxidation state in VO whole 2 plus, and titanium plus 4 oxidation state is present in TiO whole 2 plus. So basically, how we are obtaining this? We are basically obtaining the oxide upon reaction of metals with oxygen at higher temperatures. Moving down, as the oxidation number of the metal increases, ionic character decreases. Why is it so? Oxidation number increases, ionic character decreases. So in case of manganese, Mn2O7 is a covalent green oil. So Mn2O7, which is considered to be the highest oxidation state, manganese with the highest oxidation state is present in Mn2O7. Okay, they are talking about acidity current. Okay, so this Mn2O7 gives HMnO4, CrO3 gives H2CrO4 and H2Cr2O7. V2O45 is however amphoteric, though mainly acidic. It gives VO4 taken 3 minus and as well as VO2 plus salts. Vanadium, there is a gradual change from the basic V2O3 to less basic V2O4 and to amphoteric V2O5. So basically there's a lot of facts that has to be remembered in these particular passages. So first என்னதுன்னா the highest oxidation number அப்படின்றது coincides with the highest, the group number, right? Now we'll talk about oxidation number increase ஆகுது அப்படின்னா ionic character decrease ஆகுது. Yes. இப்போ Mn2O7 அப்படின்றது ஒரு covalent green oil. Okay, is that fine? And CrO3 அப்படின்றது and V2O5 இது எல்லாமே வந்துட்டு the highest oxidation states where chromium is present in +6 oxidation state, vanadium is present in +5 oxidation state and manganese is present in +7 oxidation states, right? இது எல்லாமே are the higher oxidation states. இப்போ if it has ionic character அப்படின்னா it will have a more of boiling point or melting point, whatever. ஆனால் since the crystal lattices are not that predominant in ionic character, hence they have low melting point. Yes, so that is attributed towards their low melting point. Higher oxides la acidic character is predominant. What is acidic character? The ability to produce H plus ions, adu ante acidic character. The ability to accept a pair of electrons, that is an acidic character. Bronsted acid, adu. What else do we have? We have Lewis theory as well. So இப்போ அவங்க என்ன சொல்கிறாங்க அப்படின்னா ஹையர் ஆக்சைட்ஸில் அசிடிக் கேரக்டர் அதிகமாக இருக்குது, which means that it has the ability to get reduced. The guy which get reduced, I think it's space, right? Okay, fine. Mn2O7 gives HMnO4, that is it is getting reduced. CrO3 gives H2Cr O4 and H2Cr2O7 and V2O5 is however amphoteric, so mainly acidic, and it gives rise to VO4 3 minus as well as VO2 plus salts. So அதாவது என்ன சொல்கிறாங்கன்னா Mn2O7 என்பது being acidic leads to the formation of HMnO4. Okay, and similarly we have CrO3 which gives rise to H2Cr O4 and H2Cr2O7. Yes, whereas V2O5 அப்படின்றது it can give VO2 plus as well and it can give VO4 3 minus. ஏன் அப்படின்னா he is an amphoteric oxide. In vanadium it is a gradual change from basic mediumல இருந்து V2O3 less basic V2O4 and we are obtaining amphoteric V2O5. Yes, so V2O5 is going to be amphoteric அப்படின்றத சொல்ல வரேன். V2O4 it is able to dissolve in acids. If it is able to dissolve in acids அப்படின்னா it's basically undergoing an acid base reaction and it leads to the formation of VO4 3 minus and VO4 plus. Yes, respectively. So the well characterized chromium oxide is basic but Cr2O3 is amphoteric அப்படின்றத சொல்கிறாங்க. Okay, so CrO is basic and Cr2O3 is amphoteric. God damn it, there's a lot of things to be remembered, man. But that's fine actually. We can revise it once again as we do. So potassium dichromate is a very important chemical used in leather industry and as an oxidant for preparation of many azo compounds. Although it is a very good oxidizing agent in preparation of a lot of organic compounds, and it is also used in leather industry, it seems. I don't know. Dichromates are generally prepared from chromate, which in turn are obtained by the fusion of chromite ore with sodium or potassium carbonate. அதாவது ஒரு குரோமைட் ஓர்ன்றது பேசிக்கலி இட் இஸ் ஃபெர்ரஸ் ஓர் வித் ஐ மீன் வாட் எவர் இந்த காம்பவுண்ட் இஸ் with sodium or potassium formation of chromate. Chromate learn we will obtain the formation of dichromate. Now we will see the reaction in sequence with the equations as well. That's important. So as you can see, 4 moles of FeCr2O4 plus 8 moles of sodium carbonate plus 7 moles of dioxygen gives rise to 8 moles of sodium chromate, okay, plus 2 moles of Fe2O3 plus 8 moles of carbon dioxide. The yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromate. Okay, இப்போ என்ன நடக்குதுன்றது பார்ப்போம் in a glimpse. என் பார்வை உன்னோடு உன் பொம்மை கண்ணோடு பேசாம நின்னோடு நாம் இறந்து போவோம் காதோரோ அடியாதோரோ. So basically if I have 4 moles of FeCr2O4 plus 8 moles of sodium carbonate plus 7 moles of dioxygen leads to the formation of 8 moles of sodium chromate plus 2 moles of Fe2O3 plus 8 moles of carbon dioxide. Okay. குரோமைட் ஓர்ன்றது இதுப்பா, இது வந்து சோடியம் கார்பனேட்டோட ரியாக்ட் பண்ணுறேன்ப்பா. அண்ட் ஐ எம் வந்து டூயிங் சம் ஆக்சிடேஷன்ப்பா. ஐ எம் அப்டைனிங் த குரோமேட்டுப்பா, CrO4பா. எல்லோ சொல்யூஷன் வருதுப்பா, இது வந்து எல்லோ கலராகப்பா. ஓகேவாப்பா. அண்ட் தென் ஐ எம் ஹேவிங் Fe2O3 அண்ட் ஐ எம் அப்டைனிங் கார்பன் டை ஆக்சைடு. ஓகேவாப்பா. இப்போ நான் ஐ எம் ஹேவிங் த ஸ்டைக்கியோமெட்ரிக் கோஎஃபிஷியன்ட்ஸ். இங்கே 8, இங்கே 2, இங்கே 8 moles of carbon dioxide, 8 moles of sodium chromite, and I am having 4 moles of chromite and 8 moles of sodium carbonate. So 4, 8, 7, 8, 2, 8 நல்லா இருக்கு. 4, 8, 7, 8, 2, 8 எப்படி நான் வச்சுக்கலாம். I think remembering this will be actually really useful. Remembering, learning must be pure, remembering can be dirty. I can do it in any way I want. Okay, so the yellow solution of sodium chromate is filtered and acidified with sulfuric acid. சரி ரைட்டு. ஸோ இப்போ வந்து தலைவனை வந்து அசிடிஃபை பண்ணுறாங்க to give a solution of orange sodium dichromate. ஸோ sodium dichromate வருது, orange color, which is can be crystallized. Sodium dichromate is more soluble than potassium dichromate. So the latter is therefore prepared by treating the solution of sodium dichromate with potassium. ஸோ பேசிக்கலி நம்ம என்ன பண்ணுறோம், சோடியம் டைக்ரோமேட் அப்படின்றது இட் இஸ் டர்னிங் அவுட் டு பி மோர் சால்யூபிள். டு மேக் இட் மோர் கிறிஸ்டலைஸ் we are making it react with potassium chlorate, which leads to the formation of potassium dichromate. So the reaction sequence is this. We're basically making it react, making chromite ore to react with sodium carbonate, lead to the formation of chromate. Now this particular chromate upon reaction with a dilute sulfuric acid or whatever the medium is leads to the formation of sodium dichromate, and sodium dichromate upon reaction with potassium chloride leads to the formation of potassium dichromate, and potassium dichromate has orange color. Okay, so the dichromates and dichromates are interconvertible in aqueous solution depending upon the pH of the solution. அதாவது chromates and dichromates, these are interconvertible in aqueous solution அப்படின்ற சொல்கிறாங்க. எந்த pH இருக்கோ அந்த பர்டிகுலர் pH பேசிஸில் it will be converted into chromate or dichromate respectively. The oxidation state of chromine in chromate and dichromate is the same. So chromate and dichromate பொறுத்த வரைக்கும் oxidation state is going to be the same. So sodium chromate dichromate upon reaction KCl leads to the formation of K2Cr2O7, that is potassium dichromate with the formation of sodium chloride and orange crystals. This is basically an orange crystal. Yes, and sodium chromate is a yellow solution, and sodium dichromate is also an orange. We'll have the chromate and dichromate between upon the, in appropriate conditions. Like if I have 2 moles of CrO4 2 minus upon reaction with 2 moles of H plus leads to the formation of Cr2O7 2 minus plus water. Moving on, similarly Cr2O7 2 minus in presence of a basic medium leads to the formation of dichromate, chromate ion, CrO4 2 minus plus water. So the structural description is that, okay, now we are given with the structural description of CrO4 2 minus and Cr2O7 2. ஒன்றுமே இல்லை, ஃபஸ்ட்டு CrO4 எழுதுவோம். CrO4ல we'll have oxygen, 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 oxygen are ball bonded in the 4 sides with a negative charge over it. And dichromate பொறுத்த வரைக்கும் we'll have the same structural, the difference is going to be this: there will be a chromium oxygen chromium kind of a bond which is 126 degree apart with 179 picometers. Yes, and the chromium oxygen bond, it turns out to be 163 picometers of length. So the structures of chromate ion CrO4 2 minus and the dichromate ion Cr2O7 2 minus are shown below. The chromate ion is tetrahedral, whereas the dichromate ion consists of 2 tetrahedral sharing one corner with CrOCr bond angle of 126 degree. Okay, the sodium and potassium dichromates are strong oxidizing agents. Okay, fine, which means that they get reduced easily. Sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Okay, now that we have seen the preparations, the structures, their interconvertibility, the structural descriptions, the chromate ion is tetrahedral, whereas dichromate is consisting of 2 tetrahedral with one corner shared with angle of 126 degrees, and extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis. ஸோ வால்யூமெட்ரிக் அனாலிசிஸில் நம்ம ப்ராக்டிகல்ஸ்லாம் பார்த்துருப்போம். K2Cr2O7 சொல்யூஷன்லாம் யூஸ் பண்ணிட்டு இந்த வால்யூமெட்ரிக் டைட்ரேஷன் வச்சு மொலாரிட்டி ஆஃப் அ சொல்யூஷன் கண்டுபிடிக்க முயற்சி பண்ணுவோம். அண்ட் அந்த பர்டிகுலர் ரியாக்ஷன்ஸ்லையும் வந்துட்டு இட் இஸ் யூஸ்ஃபுல். இன் அசிடிக் சொல்யூஷன் இஸ் ஆக்சிடைசிங் ஆக்ஷன் கேன் பி ரெப்ரசன்டட் as follows. Okay, so we are given with a reaction. So basically we are having for dichromate upon in acidic medium upon abstraction of 6 electrons leads to the formation of 2Cr3 plus 7 moles of water formed. That is, it has been reduced from whatever the substrate is, whatever the reduction potential is turning out to be 1.33 volts. So thus this acidified potassium dichromate will oxidize iodides to iodine. So since it has a reducing power, it is basically being able to oxidize other guys. Yes, it oxidizes iodides to iodine, sulfides to sulfur, tin 2 to tin 4 and iron 2 to iron 3. ஸோ இப்போ இங்கே பார்த்தீங்கன்னா அயோடைட்ஸை வந்துட்டு அயோடினாக மாற்றுது, சல்ஃபைட்ஸை வந்து சல்ஃபராக மாற்றுது, tin 2 வந்து tin 4ஆக கன்வெர்ட் பண்ணுது, ஆக்சிடைஸ் பண்ணுது, அண்ட் Fe2 + Fe3 +ஆக கன்வெர்ட் பண்ணுகிறார். So the full ionic equation may be obtained by adding the half reactions for potassium dichromate to the half reaction for the reducing agent. Okay, so basically we have potassium dichromate to the half reaction for the reducing agent such as Cr2O7 2 minus in acidic medium. இப்போ நான் வந்துட்டு I'm adding the half reaction 6Fe2 plus. Now this Fe2 plus is oxidized to Fe3 plus and Cr2O7 is reduced, and that's how we are obtaining the reducing whatever it is. So that's the half cell reactions added together. இப்போ வந்துட்டு I'm obtaining entering into potassium permanganate. ஸோ எப்படி பண்ணுறேன்னு பார்ப்போம். Potassium permanganate is prepared by fusion of M1O2 with an alkali metal hydroxide. So I'm seeing the preparation. Fusion of manganese oxide with metal hydroxide such as KOH and an oxidizing agent such as KNO3. This produces a dark green color K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. So basically என்ன நடக்குதுன்னா நம்மளுடைய Mn O2 MnO4 minus and MnO2. So the MnO4 minus in the particular number we are obtaining the potassium permanganate. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate 6. So என்ன நடக்குது MnO4 2 minus உடைய oxidation அப்படின்ற அந்த பேசிஸில் electrolytic oxidation in alkaline solution. So first one time fusing it in with KOH in presence of oxidizing medium such as KNO3, and then I'm using electrolytic oxidation and alkaline to the formation of an electrolytic oxidation of manganate. Yes. So oxidation of manganese 2 ion salt by okay, fine. In laboratory, this is the commercial method. So general method, general method basically we will fuse it with KOH and then we will use oxidizing agent to disproportionate it and form MnO2 minus and MnO4 minus and MnO2 respectively. Commercial method next laboratory manganese 2 ion salt is oxidized to peroxodisulfate to permanganate. என்னம்மா எனக்கு புரியல peroxodisulfate na. So in laboratory a manganese 2 ion salt is oxidized by peroxodisulfate, that is S2O8. Okay, having 2 permanganate tetrahedral manganate ion which is green in color. So potassium permanganate which forms dark purple crystals which are isostructural those of KClO4. The salt is not very soluble in water. It is about 6.4 grams per 100 grams of water, but when heated it decomposes at 513 Kelvin. Potassium permanganate at 513 Kelvin, it's basically not soluble in water. It is I think it's a green colored structure. Upon doing it can form a dark purple color structure crystals of KClO4 which is isostructural to that of KClO4. Find it. And the salt is not soluble, heated and considerable interest, the intense color and its diamagnetism along with the temperature dependent weak paramagnetism. This can be explained by the use of molecular orbital theory. Temperature dependent slight paramagnetism takes place by overlap of p orbitals of oxygen with d orbitals of manganese. That is manganate and permanganate, they both are tetrahedral in structure. The overlap of p orbitals of oxygen and d orbitals of manganese நடக்கும் அப்படின்ற சொல்றாங்க. Pi bonding எப்படின்னா the pi bond takes place due to the overlap of p orbitals of acidic permanganates oxidizes to ion 3 nitrates and iodides to free iodine. So this guy has a iodine. By half reactions. By half reaction. So at concentration of H plus is equal to 1 given. The hydrogen ion concentration of the solution plays an important role in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Manganate at concentration of H plus is equal to 1 should oxidize water, but in practice the reaction is extremely slow. Fine, now we'll have to talk about a lot of oxidizing reactions of KMnO4. Yes, we have really a lot of reactions to do. Oh my god. கடவுளே ஏன் என்னை சோதிக்கிறாய்? Let me just see these reactions after some time, bro. I'm really fed up. Okay, I think I will be able to obtain the reactions. preparative organic chemistry for the bleaching of wool, cotton. Okay, now we are entering into the inner transition elements, the F block elements. The F block consists of two series, lanthanides, the 14 elements following lanthanum, and the actinides, the 14 elements following the actinium. Because lanthanum closely resembles the lanthanoids, it is actually included in any discussion of the lanthanides, for which the general symbol Ln is often used. அதாவது லாந்தனைட்ஸோட ஜென்ரல் சிம்பிள் இஸ் Ln and lanthanum has a symbol of La. Similarly, the discussion of the actinoids includes actinium besides the 14 elements constituting the series. The actinoids அப்படின்றது though it is not, we'll include actinium in the discussion of actinoids since it is closely resembling the elements in that particular series. So the lanthanides resemble one another more closely than do the members of ordinary transition elements. So lanthanides இருக்கிற elements they are going to be closely related to each other. They have only one stable oxidation state and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. அதாவது only one oxidation state தான் ஸ்டேபிளாக இருக்க போது, and it will be an excellent opportunity for us to examine the effect of small changes in size. அதாவது சின்ன சின்ன சேஞ்ச் இன் சைஸ் அண்ட் நியூக்ளியர் சார்ஜ்னால வாட் வில் பி த எஃபெக்ட் அப்படின்றத பற்றி இந்த பர்டிகுலர் சீரீஸ் படிக்கிற மூலியமாக தெரிஞ்சுக்க முடியும். பிகாஸ் that's how the series is actually is. The chemistry of the actinoids is, on the other hand, much more complicated. The complication arises partly owing to its occurrence of wide range of oxidation state. So the lanthanides பொறுத்த வரைக்கும் only one stable oxidation state, and we will have a variety of we will examine how chemical properties changes according to the change in very small details such as atomic radii, atomic size, the oxidation state and something like that, the nuclear charge, something like that. On the other hand, the actinoids are going to be more complicated because that their occurrence of there are a lot of oxidation states in which the actinoids are present, and partly because their radioactivity creates special problems. So we'll have to discuss them in separate topics. So the name, symbols, electronic configurations of atomic and ionic states and atomic and ionic radii of lanthanum and lanthanoids, for which the general symbol Ln is used, are given. So electronic configurations பார்ப்போம். It may be noted that the atoms of these elements have electronic configurations with 6s2 common but variable occupancy of 4f level. However, the electronic configuration for all the tri-positive ions, the most stable oxidation states, are of the form 4Fn. N is equal to 1 to 14. அதாவது 6s2 is going to be common, ஆனால் the number of electrons in the f orbital is going to vary from 1 to 14, but the plus 3 positive, the tri-positive cation is going to have 4Fn configuration with the number of electrons varying from 1 to 14. Now we'll talk about atomic and ionic sizes. The overall decrease in atomic and ionic radii from lanthanum to lutetium, the lanthanide contraction, is a unique feature in the chemistry of lanthanides. So lanthanides பொறுத்த வரைக்கும் lanthanum வந்து lutetium வரைக்கும் we are going to have a general decrease in the sizes. So there's no I don't think there will be any anomalous behavior up and over here. There's far reaching consequences in the chemistry of the third transition series of the elements. Okay, the decrease in the atomic radii derived from the structures is not quite regular as it is regular in the tri-positive ions. So tri-positive ions பார்க்கும்போது it is very very regular, ஆனால் இந்த decrease in atomic radii பார்க்கும்போது it's not going to be that stable அப்படின்ற சொல்கிறாங்க. This contraction is of course similar to that observed in an ordinary transition series and is attributed to the same cause, the imperfect shielding. So basically our ordinary transition seriesல என்ன மாதிரியான ஒரு ப்ராப்ளம்ஸ்லாம் வருமோ, என்னென்னலாம் எஃபெக்ட்ஸ்னால காசஸ்னால இந்த பர்டிகுலர் எஃபெக்ட் வரும். அதாவது imperfect shielding of the 4f electron by one another is less than that of the shielding by 1d electron by the another with increase in the nuclear charge. So there is fairly decrease in sizes with increasing atomic number. The cumulative effect of the contraction of the lanthanide series, known as lanthanide contraction, causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. Okay, so அதாவது என்ன சொல்ல வராங்க, the cumulative effect of the contraction of the lanthanide series, known as the lanthanide contraction, causes the radii of the members of the third transition to be very similar to that of the corresponding members of the second series. Our third series ko second series ko they will be having a same the almost identical radii of zirconium and hafnium A consequence of the lanthanide contraction account for their occurrence together in nature and for the difficulty faced in the separation. And நம்ம பார்க்கும் பொழுது zirconium and hafnium, though they are present in the second and third series of the transition elements respectively, these guys are actually having similar atomic radii, and it is due to this particular reason that they are occurring in nature in together, as well as they are, will face a difficulty in separating them அப்படின்ற சொல்கிறாங்க. So trends in ionic radii of lanthanides. Okay, as you can see, the trends is very regular in case of tripositive ion. Moving down oxidation states, in the lanthanides, La2 and Ln3 compounds are predominant species. However, occasionally +2 and +4 ions in solution or in solid compounds are also obtained. Now we are talking about oxidation states. Okay, fine. How much ever it's going on? God damn it. Yeah, I have 5 pages to go. I think I'm in the first page. 5 more pages to go. Yes, I think we can do this. So in the lanthanides, lanthanum 2 and lanthanum 3 compounds are predominant species. However, occasionally +2 and +4 in solutions or in solid compounds are also obtained. அதாவது predominant species வந்து second and third +2 and +3, now +4 and +2 are also obtained in solutions. Okay, this irregularity as in ionization enthalpy arises mainly from the extra stability of empty half filled or filled F subshell. அதாவது இந்த irregularityயோடைய காரணம் என்ன அப்படின்னா extra stability of empty half filled or filled F subshell. Thus the formation of cerium-4. Cerium +4 is favored by its noble gas configuration, but it is a strong oxidant reverting to the common +3 state. The common electrode potential value for cerium-4 plus to cerium-3 plus is +1.74, which means that it is favorable for its reduction towards cerium-3 plus. Okay, it's a very strong oxidant reverting to the common 3. Okay, which suggests that it can oxidize water. Since it is a very good oxidizing agent, which means that it gets reduced. அதாவது cerium-4 அப்படின்றது, though it has a noble gas configuration. Oh my god, India. Okay, fine, moving on. So cerium-4 is having a noble gas configuration. Since its electrode potential value from turning towards 4 plus to 3 plus is +1.74, it is basically reverting back to its common +3 oxidation state. However, the reaction rate is very slow, and cerium-4 is a good analytical reagent. Otherwise, the reaction is going to be very slow, and it seems like that cerium-4 is used as an analytical reagent, which means that oxidation purposes or something like volumetric purposes, we'll have the usage of cerium. Praseodymium, neodymium, terbium, dysprosium also exhibits +4 state, but only in its oxides. Fine, great. So MO2 in a particular oxide, it is able to show the +4 oxidation state. Europium 2 plus is formed by losing the 2 s electrons, and its F7 configuration accounts for the formation of this ion. Basically europium 2 plus in configuration, why is it favored அப்படின்னா, it is due to the fact that it is having F7 configuration, the half-filled configuration of F orbital. However, europium 2 plus is a strong reducing agent, changing to its common +3 state. அதாவது which means that it will be getting oxidized to form its common +3 state. Similar, ytterbium 2 plus, which has F14 configuration, is a reductant. Okay, which means that it is a reducing agent. That means it gets oxidized. Okay, fine. Sorry for the inconvenience. Let's just continue. So there's a lot of facts to be remembered in this particular passage. So first things first, let me just try summing it up. Lanthanum 2, lanthanum 3 are the most common predominant species. and occasionally we'll obtain the plus 2 and plus 4 ions in solution, and there's an irregularity due to the extra stability of empty, half-filled or fully filled F subshells. And okay, moving on. The formation of cerium-4 is favored by the noble gas configuration, but still it reverts back to its plus 3 configuration, which means that it will be acting as an oxidizing agent, and it will be able to oxidize water because it's having an electron potential of plus 1.74, and the reaction rate is going to be still be slow. So if it is slow reactant rate irundha, appo kandipa it can be used as an analytical reagent. And moving on, we'll have the reaction. Okay, praseodymium, neodymium, terbium, dysprosium, இது எல்லாத்துக்குமே வந்துட்டு plus 4 oxidation statesலாம் it will be obtained in its oxides MO2 like PrO2, NdO2, TbO2, DyO2. Europium 2 plus அப்படின்றது it is formed by losing to a F electron, and it stays in the configuration of F7, but still it will act as a strong reducing agent, and it reverts back to its plus 3 oxidation state. Plus 2 oxidation state, it goes on to become plus 3 oxidation state. I think that's what they're trying to say. And ytterbium similarly will act as a reductant. And terbium 4 will have half-fill of f orbitals, and it will act as an oxidant, which means it gets reduced. It can accept a pair of electrons, or it can accept electrons. The behavior of samarium is very much like europium. It will exhibit both plus 2 and plus 3 oxidation states. That's what they're trying to say, and that we are being given with the electronic configuration of each and every element in the lanthanoid series. Okay, first electronic configurations and radium of lanthanum and lanthanoids. Fine. Lanthanum with an atomic number 57 has a configuration of 5d16s2. Yes, which means that there is no F electrons present in this particular lanthanum because it's a transition element present in D block. Whenever we are having a discussion about lanthanoids, we'll always include lanthanum because it's closely resembling the lanthanoids present. So next we'll move on to cerium. Cerium it has a atomic number 58, has the 1 electron, 4f1, 5d1, 6s2. And praseodymium it jumps. It is expected to have 4f2, 5d1 configuration, but it turns out to have 4f3, 6s2. And similarly we have neodymium it is expected to have 4f3, 5d1, 6s2 configuration, but it's formed to have 4f4. And we have promethium 4f5, samarium 4f6, europium 4f7, gadolinium 4f7, 5d1, terbium 4f9. So basically in the expected series gadolinium is the only one which is accomplishing that expected electronic configurations. The rest of all will never have a d electron, and gadolinium and adhe mari lutetium. So என்னென்னலாம் எக்ஸ்பெக்டடாக ஃபுல்ஃபில் பண்ணுதோ தட் இஸ் சீரியம், கேடோலினியம் அண்ட் தென் லுட்டீஷியம். மற்ற எல்லா எலக்ட்ரான்ஸுமே மற்ற எல்லா எலிமெண்ட்ஸ்லையுமே வந்துட்டு த டி எலக்ட்ரான் இஸ் பேசிக்கலி ஷிஃப்டட் பேக் டுவர்ட்ஸ் த எஃப் ஆர்பிட்டல். In case of praseodymium, neodymium, promethium, samarium, europium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. Yes, so that's how the things are going to be. I don't think I will be able to remember them all. I'm just trying to remember the sequence. So I'm just trying, let me just say it once again. Lanthanum is, I'm not going to include. Next I will start with cerium, praseodymium, neodymium, promethium, samarium, that's all I remember. Next we will go to Europe, gadolinium, terbium, dysprosium. Terbium is given Tb, dysprosium is given Dy, holmium is given Ho, erbium is given Er, thulium is given Tm, and ytterbium is given Yb, and we have finally lutetium with Lu configuration. Lu, that's the symbol. Moving down, we have the general characteristics. The general characteristics are oh my god, we have 4 more pages to go. God damn it. Fine, we can do this. General characteristics: all the lanthanoids are silvery white soft metals and tarnish rapidly in air. The hardness increases with the increase in atomic number, samarium being steel hard. So what they're trying to say is that they look as that they have a silvery white appearance, and they are soft metals, and they become harder with their increasing atomic number, and samarium will be having a steel hard physical property. Okay, fine. Moving on. The melting points range between 1000 to 1200 kelvins, but samarium melts at 1623 kelvin. Okay. So ஏன் சம்மேரியம் பற்றி பேசணும் அப்படின்னா சம்மேரியம் ஐ திங்க் இட் ஹேஸ் நியர்லி half fill configuration of 4f6. They have typical metallic structures and are good conductors of heat and electricity. So basically these are the guys will have typical metallic structures and they are good conductors of heat and electricity. Density and other properties change smoothly except for europium ytterbium, occasionally for samarium ytterbium. So no, it's not terbium, it's actually thulium. Okay, இப்போ என்ன சொல்ல வராங்கன்னா melting point is going to range between 1000 to 1200 kelvins, but samarium it's going to melt at 1623 kelvins due to the fact that it is having more number of unpaired electrons, which means that it will be having a lot of intermolecular interactions between them. And then their metallic structure, okay fine, that's fine. And the density and the properties, they have a smooth transition from, but except for europium ytterbium, the density and other properties are going to be smooth and that's going to change smoothly. Moving down, we have many trivalent lanthanide ions are colored both in the solid state and in aqueous solutions. Now we are talking about color. Ions sort of colors பத்தி பார்க்க போறோம். And what they're saying is that they are only colored in the solid and aqueous solutions. Color of these ions may be attributed to the presence of F electrons. So why is it so? Due to the presence of F electrons, neither lanthanum 3+ or lutetium 3+ shows any color, but the rest do so. Okay, fine. What they're trying to say is that lanthanum 3+ and lutetium 3+ will not show any color due to the absence of an electron, but rest do shows because they are having electrons for excitation and de-excitation. And okay, fine. However, absorption bands are narrow, probably because of the excitation within F level. Okay, absorption bands are narrow. Okay, what they are trying to say, because of excitation within F level, அதாவது F லெவல்குள்ளேயே வந்துட்டு the absorption நடக்கிறன்ற காரணத்தினால, which means that there is no scope for further absorption occurring. It is due to that particular factor the absorption levels are narrow. The lanthanide ions other than F0 type, that is lanthanum 3+ or cerium 4+, and F14 type like ytterbium 2+ and lutetium 3+ are all paramagnetic. அதாவது இந்த லாந்தனம் மற்றும் லுட்டீஷியம் தவிர மற்ற எல்லாருமே ஆர் கோனா பி பாராமேக்னெட்டிக் அப்படின்றத சொல்கிறாங்க. The first ionization enthalpies of the lanthanides are around 600 kilojoules per mole, the second about 1200 kilojoules per mole, comparable with those of calcium.
Guys, பாத்துட்டு இருக்க எல்லாரும் மறக்காம subscribe பண்ணிருங்க. ஏற்கனவே பஞ்சத்துல அடி விட்டுட்டு இருக்கோம்.
யாருமே பார்க்க மாட்டாங்க.
1 view இருக்குடா.
யாரும் நடுவில் 2 வியூ வந்துச்சு, யாரும் தெரியல.
ஒன்னால பார்க்க முடியல. யார் வியூ பண்ணாலும் கூட. பார்த்தவங்க மறக்காம கமெண்ட் பண்ணிருங்க. லைக், ஷேர் அண்ட் சப்ஸ்கிரைப்.
நீ தான் பண்ணணும், நீ மட்டும் தான் பார்த்து
பண்றேன்டா. நான் சப்ஸ்கிரைப் பண்ணல.
டிவிடி அப்ப
நல்லா சப்ஸ்கிரைப் பண்ணா யூடியூப் மியூசிக் ஆப்ஷன்டா.
ஓகேடா. ஓகேடா. ஓகேடா.
பேசாம நீ ட்விட்டர் ஆயிடுறா. நான் காசு செம்மையா சம்பாதிக்கலாம். சத்தியம் சொல்றேன். ஐஐடி போய் எதுக்கு 4 வருஷம் படிச்சுக்கிட்டு 11th 12th அப்படி 11th 12th நடத்திட்டு இருக்கல, சைடு பை சைடு ஐஐடி படி. லைவ்ல இருக்கே
எவனும் பார்க்க மாட்டான், அதுவும் லைவ் கடைசிக்கு வந்துருச்சு. Moving on, the first ionization enthalpies of the lanthanides are around 600 kilojoules per mole. I'm going to talk about the chemical properties. So ionization enthalpy, first ionization enthalpy it will range between 600 and second ionization enthalpy will range about 1200, comparable with those of calcium. A detailed discussion of the variation of the third ionization enthalpy indicates that the exchange enthalpy considerations appear to impart a certain degree of stability to the empty, half-filled and completely filled orbitals. Okay, this is indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gadolinium and lutetium. அதாவது என்ன சொல்ல வராங்க, a discussion in detailed discussion about the third transition levels, third transition enthalpy, variation in the third ionization enthalpy indicates the exchange enthalpy consideration appear to impart a certain degree of stability to the empty. Okay, this is indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gadolinium and lutetium. Their chemical behavior in general, the earlier members of the series are quite reactive, similar to calcium, but with increasing atomic number, they behave more like aluminium. அதாவது கெமிக்கல் பிஹேவியர் ஜென்ரலாக பார்க்கும்பொழுது ஏர்லியர் மெம்பர்ஸ் ஆஃப் த சீரீஸ் ஆர் குவைட் ரியாக்டிவ் அப்படின்னு சொல்கிறாங்க. இட் இஸ் சிமிலர் டு தட் ஆஃப் கால்சியம். வித் இன்க்ரீசிங் அட்டாமிக் நம்பர் தே பிஹேவ் மோர் லைக் அலுமினியம். ஓகே, வாட் தே ஆர் ட்ரைங் டு மீன் ஓவர் ஹியர்? ஸோ வேல்யூஸ் ஆஃப் ஸ்டாண்டர்ட் எலக்ட்ரோபொட்டன்ஷியல் ஃபார் த ஹாஃப் ரியாக்ஷன்ஸ் are in the range of -2 to -2.2 to -2.4 volts except for europium, which is having a -2 volt. Okay, so as you can see, lanthanum 3 plus is actually accepting a 3 electrons to form lanthanum 3, lanthanum neutral, lanthanum solid. Okay, increasing atomic number, behave more like aluminium, fine grade. This is of course a small variation. The metals combine with hydrogen when gently heated in the gas. The carbides, lanthanum carbide, okay, Ln3C, Ln2C3, Lnc2 are formed when the metals are heated with carbon. Okay, so they are talking about formation of carbides. So basically the range of electropotential value half cell reaction oda value kuduthirukanga, that is for accepting electrons. Reduction potential values kuduthirukanga. And then this is of course a small variation. The metals combine with the hydrogen when gently heated in the gas, and then so as you can see, upon using gases, it basically, okay, fine, great. When gently heated in the gas, the carbides Ln3C, Ln2C3 and Lnc2 are formed when the metals are heated with carbon. They liberate hydrogen from dilute acids, burn in halogens to form halides. Okay, they form oxides M2O3 and hydroxides MOH taken thrice. So oxides they will be forming M2O3 and the hydroxides are MOH taken thrice. The hydroxides are definite compounds, not just hydrated oxides. They are basic like alkaline earth metal oxides and hydroxides. So basically என்ன சொல்கிறாங்க, இதெல்லாம் ஹைட்ரோஜனோட கம்பைன் ஆகும், கார்பனோட கம்பைன் ஆகும் to form Ln3C, Ln2C3 and Lnc2. They will be able to liberate hydrogen from the dilute acids as they can be okay, fine, and burn in halogens to form halides. Okay, fine, great, that is also fine. And they will be able to form oxides of the form M2O3 and hydroxides of the form MOH taken thrice. The hydroxides are definite compounds, not just hydrated oxides. Okay, they are basic like alkaline earth metal oxides and hydroxides. The general reactions are depicted in figure 8.7. Figure 8.7 papom, I have lanthanum upon reaction with an acid will be able to liberate hydrogen, and upon reaction with the halogens will lead to the formation of halides LnHX3, and upon reaction with water leads to the formation of a respective hydroxide MOH taken thrice, and upon reaction with carbon at 2773 Kelvin leads to the formation of Lnc2. Heated with nitrogen leads to the formation of Ln, capital N, and heated with sulfur leads to the formation of Ln2S3, and upon oxidation, burning on oxidation leads to the formation of M2O3 அப்படின்ற type of formation நடக்கும். Rest, so oxygen and sulfur will be same kind of things, and nitrogen it will just add up because Ln3 plus and nitrogen will be a negative cation, something like that. Now that particular reaction will lead to the formation of Ln, 1-to-1 correspondence. So let's talk about the uses. The best single use of the lanthanides is the production of alloy steels for the plates and pipes. A well-known alloy is mish metal. So இப்போ வந்துட்டு மிஷ் மெட்டல்ன்ற பற்றி பார்க்க போகிறோம். It is going to consist of a lanthanoid metal about 95% and iron of 5% with the traces of silicon, carbon, calcium and aluminium. So mish metal அப்படின்றது it is a combination of 95% of a lanthanoid metal with iron of 5% and traces of sulfur, carbon, calcium and aluminium. A good deal of mish metal is used in magnesium based alloy to produce bullets, shell and lighter flint. Mixed oxides of lanthanides are employed as catalysts in petroleum cracking. Some individual lanthanide oxides are used as phosphors in television screens. So the uses என்னன்னா production of alloys, mish metal அப்படின்ற ஒரு முக்கியமான metal which is used in the production of bullets, shells, lighter flints, and mixed oxides. Lanthanides oda mixed oxides it is used as catalyst for petroleum cracking அப்படின்ற சொல்றாங்க. So these are the certain uses. Moving down, we'll talk about actinides. Now that we have seen about lanthanides, we'll see about actinides, and finally we'll have the uses and applications of DNF block elements. Cut. Damn it, we have lot. Yeah, we can further push it up. The actinoids include the 14 elements from thorium to lawrencium. The names, symbols, and some properties of these elements are given in table 8.1. I mean, table 8.10. So, this is the sequence in which I used to remember the lanthanoids. So, we have actinium, thorium, protactinium, actinium, thorium, protactinium, and then we'll have the elements of three countries. Three planets: uranium, neptunium, and plutonium in the same order. And then we'll have americium, it's a country, and curium and berkelium are two scientists, and californium, it's another country, another place, and instanium, fermium, mendelevium, nobelium, and lawrencium are few scientists, and that's how I'm gonna remember them. Actinium, thorium, and protactinium. Actinium starts with 89 and it ends at lawrencium. Lawrencium is gonna have a lawrencium, it's at 103. So actinium is 89, and then we have protactinium, thorium, and then protactinium, and then we'll have uranium, neptunium, plutonium, and then have americium. Kaduthu we'll have curium and berkelium. Kaduthu we'll have californium. Kaduthu we'll have scientists. The scientist or name ஞாபகம் கஷ்டம். E kaduthu F kaduthu M kaduthu N kaduthu L actually should come first, but இங்கே வந்துட்டு LMN க்கு பதிலா MNL அப்படின்னு வருது. EF MNL அப்படின்னு ஞாபகம் வச்சுக்க போகிறேன். ஸோ einsteinium, fermium, mendelevium, MNL, mendelevium, nobelium, and we'll have lawrencium. So actinium AC, thorium TH, protactinium PA, uranium U, neptunium NP, plutonium PU, americium AM, curium CM, berkelium BK, californium CF, einsteinium ES, fermium FM, mendelevium MD, nobelium NO, and lawrencium LR. Now let's talk about the electronic configurations. Okay, so electronic configurations பொறுத்த வரைக்கும் ஆக்டினியம், தோரியம், அப்புறம் நம்ம நெப்டினியம் வரைக்கும் வந்துட்டு we are having the expected configuration அப்படின்னு சொல்ல முடியாது. ஆக்சுவலாக expected சொல்ல முடியாது because in protactinium we are having a deviation, and from there on from plutonium, god damn, so plutonium, americium will have something, and curium is the only lone warrior with the at expected electronic configuration, and then we'll have 5f19, 5f10, 5 9 10 11 12 13 14. so இது எல்லாமே group together, and the final guy lawrencium. so curium and lawrence இவங்க ரெண்டு பேரையும் சேர்த்து இவங்க ரெண்டு பேரும் தான் will have the expected electronic configuration, and இங்கே வந்து பார்க்கும்பொழுது cerium, gadolinium, and lutetium will have the expected electronic configuration. Moving down, the actinoids are radioactive elements, and their earlier members have relatively long half-lives. The latter ones have half-lives values ranging from a day to 3 minutes for lawrencium. Okay, the latter members could be prepared only in nanogram quantities. These facts render their study more difficult. So electronic configuration, all the actinoids are believed to have the electronic configuration of 7s2 and variable occupancy of 5f and 6d subshells. Okay, the 14 electrons are formally added to 5f, though not in thorium. Thorium mattum, but from protactinium onwards, the 5f orbitals are complete at element 103. The irregularities in the electronic configurations are like those in the lanthanoids are related to the stabilities of F0, F7, F14 occupancies of the 5f orbitals. Thus the configurations of americium and curium are 5f7 7s2 and 5f7 61 7s2. Although the americium and curium, okay, although the 5f orbitals resemble the 4f orbitals in their angular part of the wave function, they are not as buried as 4f orbitals, and hence 5f orbitals can participate in bonding to a far greater extent. So ionic sizes, the general trend in the lanthanoids is observable in the actinoids. So general trend lanthanoids la irukko adhe trend da. The gradual decrease in size of tripositive ions across the series, this may be referred to as the actinoid contraction. The contraction is however greater from element to element in this series, resulting from poor shielding of 5f. So basically contraction is going to be higher due to the poor shielding of 5f electron. There is a greater, okay, next oxidation states. There is a greater range of oxidation state which is in part attributed to the fact that 5f 6d and 7s2 7s levels are of comparable energies. ஸோ இந்த கிரேட்டர் ரேஞ்ச் ஆஃப் ஆக்சிடேஷன் ஸ்டேட்ஸ்க்கான காரணம் என்னென்னா 5F 6S 7D இது எல்லாத்துக்குமே gonna have when 6D 7S are all gonna have a relatively same amount of energies. So the known oxidation states of actinides are listed in table 8.11. The actinides show in general +3 oxidation state. The elements in the first half of the series frequently exhibit higher oxidation states. For example, the maximum oxidation state increases from +4 in thorium to +5, +6, +7 respectively in protactinium, uranium and neptunium. ஸோ அதாவது ஜென்ரலாக வந்துட்டு +3 ஆக்சிடேஷன் ஸ்டேட் தான் இருக்க போகுது. ஆனால் ஃபஸ்ட் ஹாஃப் ஆஃப் சீரீஸ் வந்துட்டு இட் வில் எக்ஸிபிட் ஹையர் ஆக்சிடேஷன் ஸ்டேட் ஆஸ் வி ஹவ் சீன் இன் transition elements. And then for example, the maximum oxidation states increases from +4 in thorium to +5, +6, +7 respectively in protactinium. So till up to neptunium varakum will have +7 oxidation state, and adukapram it decreases in succeeding elements. The actinides resembles the lanthanides in having more compounds in +3 than in +4. ஸோ ஆக்டினைட்ஸில் எப்படி நம்ம லாந்தனைட்ஸில் எப்படி பார்த்தோம், தோ தேர் இஸ் அ ப்ரெசன்ஸ் ஆஃப் half filled configuration, it prefers to be in +3 configuration. Similarly இங்கேயும் அதே தான், +3 configuration is resembling and its present is attributed more. So however +3 and +4 ions tend to hydrolyze. So because the distribution of oxidation states among the actinoids is so uneven and so different from the former and the later elements, it is unsatisfactory to review their chemistry in terms of oxidation state. So oxidation state அப்படின்றது it is completely varying. There's no there is variation occurring time to time, even for same element, same oxidation states it can vary. அப்படின்ற காரணத்தினால் we cannot talk its chemistry in terms of its oxidation states. Moving on, the general characteristics and comparison with lanthanoids. The actinoid metals are all silvery. So அதே மாதிரி like how we have seen in white silvery appearance இருந்ததோ lanthanoids same. So the structural variability is obtained due to irregularities in the metallic radii which are far greater than in lanthanoids. அதாவது structural variability ஏன் அப்படின்னா basically there is irregularity in metallic radii and the metallic radii is far greater than that in seen in lanthanoids ன்னு சொல்றாங்க. So the actinoids are highly reactive metals, especially when finely divided. The action of boiling water on them, for example, gives a mixture of oxide and hydrate, and the combination with most non-metals takes place at moderate temperatures. Hydrochloric acid attacks all the metals, but most are slightly affected by nitric acid owing to the formation of protective oxide layers. Alkalis have no action. அதாவது ஹைட்ரோக்ளோரிக் ஆசிட் அப்படின்றது இட் அட்டாக்ஸ் ஆல் மெட்டல்ஸ் பட் மோஸ்ட் ஆர் ஸ்லைட்லி அஃபெக்டட் பை நைட்ரிக் ஆசிட் ஓயிங் டு த ஃபார்மேஷன் ஆஃப் ப்ரொடக்டிவ் ஆக்சைட் லேயர்ஸ். ஆல்கலிஸ் ஹவ் நோ ஆக்ஷன். ஸோ இப்போ இதோடைய ரியாக்டிவிட்டிஸ் பற்றி பார்ப்போம். ஃபஸ்ட்டு தீஸ் ஆர் வெரி ஹைலி ரியாக்டிவ் மெட்டல்ஸ். பாய்லிங் வாட்டரில் ரியாக்ஷன் நடக்கும்போது இட் வில் ஃபார்ம் அஸ் ஆக்சைட் அண்ட் ஹைட்ரேட் மிக்சர் வித் அ காம்பினேஷன் வித் மோஸ்ட் நான் மெட்டல்ஸ் டேக்ஸ் பிளேஸ் அட் மாடரேட் டெம்பரேச்சர். நெக்ஸ்ட்டு ஹைட்ரோக்ளோரிக் ஆசிடில் வந்துட்டு தேர் வில் பி slightly affected by hydrochloric acid nala there will be affection, but nitric acid nala there will be slight affection due to the formation of protective oxides, and alkalis nala there is no action அப்படின்ற சொல்றாங்க. Okay, moving down, the magnetic properties of the actinoids are more complex than those of the lanthanoids. Although the variation in the magnetic susceptibility of the actinoids with the number of unpaired 5f electrons is roughly parallel to the corresponding results for the lanthanoids, the latter have higher values. It is evident from the behavior of the actinides that the ionization enthalpies of the early actinoids, though not accurately known, but are lower than for the early lanthanoids. This is quite reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of the electrons. அதாவது என்ன சொல்ல வராங்க அப்படின்னா, behavior of the actinoids that the ionization enthalpy of the early actinoids not accurately known are lower. ஏன் அப்படின்னா 5f orbitals are beginning to be occupied, they will penetrate less into the inner core, which means that it will be easier for us to remove a 5f electron rather than removing a 4f electron, which means that it will be having a lesser it will be easier for us to remove a 5f electron அப்படின்றதான் சொல்ல வராங்க. So because the outer electrons are less firmly held, they are available for bonding in the actinoids. A comparison of the actinoids with the lanthanoids with respect to the different characteristics as discussed above reveals that the behavior similar to that of lanthanoids is not evident until the second half of the actinoid series. அதாவது என்ன சொல்ல வராங்க, with respect to different characteristics reveals that behavior similar to that of lanthanoids is not evident until the second half of the actinoid series. However, even the early actinoids resemble the lanthanoids in showing close similarities with each other and in gradual variation. So basically it is not evident until the second half, அதாவது அவங்க 2 பேரும் சேம் கேரக்டர்ஸ் காட்டுறாங்களா அப்படின்னு பார்த்தா செகண்ட் ஹாஃப் வரைக்கும் தேர் இஸ் நோ எவிடன்ஸ் அப்படின்னு சொல்கிறாங்க. ஆனாலும் இயர்லி ஆக்டினாய்ட்ஸ் தே ரிசம்பிள் த லாந்தனாய்ட்ஸ் இன் தே வில் ஹாவ் க்ளோஸ் சிமிலாரிட்டிஸ் அண்ட் தே வில் ஹாவ் கிராஜுவல் வேரியேஷன்ஸ் இன் ப்ராப்பர்ட்டிஸ் விச் do not entail change in the oxidation state. The lanthanoid and the actinoid contraction have extended effects on the sizes and therefore the properties of the elements succeeding them in their respective periods. The lanthanoid contraction is more important because the chemistry of elements succeeding the actinoids are much less known at the present time. இப்போ என்ன சொல்ல வராங்கன்னா லாந்தனாய்ட் ஆக்டினாய்ட் கான்ட்ராக்ஷன் 2 விஷயங்கள் நடக்குது. இந்த பர்டிகுலர் கான்ட்ராக்ஷன் காரணமாக அதோட சைஸ்னால எஃபெக்ட் இருக்குது. அண்ட் சைஸ் எஃபெக்ட்னா இப்போ கண்டிப்பாக the properties of the elementsலையும் there will be certain effect அப்படின்னு சொல்கிறாங்க. அண்ட் the lanthanoid contraction is of more importance. ஏன்னா it is more important because actinoids பற்றி we do not know much about at this particular time அப்படின்றத சொல்கிறாங்க. So name a number of the lanthanoids which is well known to plus exhibit plus 4 oxidation state is cerium. Okay, actinoid contraction is greater from element to element because very well shielding effect due to the 5f orbitals. Now we are entering into the final part of this particular chapter and then we will finish off a wrap up our session. So iron and steels are most important construction materials. Their protection is based on the reduction of iron oxides, the removal of impurities and the addition of carbon and alloying metals such as chromium, manganese and nickel. அதாவது iron and steel, these are important construction materials. It is based upon the reduction of iron oxide, the removal of impurities and the addition of carbon and alloying metals such as chromium, manganese and nickel. இந்த மாதிரி சில முக்கியமான இடங்கள்லாம் இந்த அயனுடைய பயன்பாடு என்பது ரொம்ப ரொம்ப அவசியமாக இருக்கிறதா சொல்கிறாங்க. Some compounds are manufactured for special purposes such as TiO for pigment industry, MnO2 for use in dry battery cells. The battery industry also requires zinc and nickel or cadmium. These elements of the group 11 are still worthy of being called the coinage metals. Although silver and gold are restricted to collection items and the contemporary UK copper coins are copper coated steel. The silver UK coins are copper or nickel alloy. Many of the metals and or their compounds are essential catalysts like V2O5 catalyzes the oxidation of SO2 in manufacture of sulfuric acid. TiSiO4 with AlCH3 taken thrice forms the basis of the Ziegler-Natta catalyst and manufacture of polyethylene, that is polythene. Iron catalysts are used in Haber process for the production of ammonia. Nickel catalysts enable the hydrogenation of fats to proceed. Wacker process the oxidation of ethane to ethanol and is catalyzed by palladium chloride. Nickel complexes are useful in the polymerization of alkanes. And photographic industry relies on the AGBR. So in the Wacker process we'll have the usage of palladium chloride. Polymerization of alkanes வந்து நிக்கலோடைய முக்கியமான பங்கும். Photographic industry we have AGBR. TaCl4 with aluminum CH3 taken thrice will form the basis of the Ziegler-Natta catalyst and V2O5 catalyzes the oxidation of sulfur dioxide. And இதை தவிர்த்து we will have MnO2 used in dry battery cells and TiO used in pigment industry. இதெல்லாம் வந்து is the important usages of the DNF block elements, and with that we are signing off with the DNF block elements. Seeing you in the next session for coordination compounds.